Very good. So this is largely going to be a presentation of this paper, and this paper presents some of these ideas in a very particular setting where we can ask all of these similar questions, and whatever we say here is, I mean, if we say something here, we should say the same thing in the context of the black hole. So keep that in mind, and I'll try to make that analogy here. Okay, so just to emphasize that this set of lectures was called Closed Universes versus AdS CFT, and that statement is really the statement of the factorization problem. So the main thing that we're missing here or not understanding in the gravitational path integral in the context of AdS CFT is really this factorization problem. And just to emphasize again what that is, we can have completely closed AdS boundaries, asymptotic AdS boundaries, which can have connected solutions, which are these wormholes. So these are what I was earlier drawing as these blue circles. Think of these as some manifold in whatever dimension you like, some d-dimensional manifold which is closed. And then you can have solutions which interpolate between one boundary and another boundary in some connected manner. This on its own would have computed some ZCFT, and this thing would have also computed some ZCFT, which of course are numbers. And so it's weird that there's this connected contribution. There's obviously disconnected contributions that contribute to ZCFT itself. But what this essentially says is that ZCFT times ZCFT with this angle bracket meaning to the path integral is not equal to the product of ZCFT and VCFT. Right? Just because there seem to exist these connected contributions, and unless they cancel, it's not clear. So that's really the puzzle. Now, let me just tell you of concrete setups where this has been discussed. There's a long history to this, and actually giving these lectures helped me deep dive into some of those things. It's very helpful to just talk about that a little bit. So, a very clear presentation of this was presented by Mardasena and Maus, where they constructed some such solutions. And the easiest way to construct solutions like this is you basically have a hyperbolic slicing. So if you look at a d+1 dimensional hyperbolic manifold, we slice it as 0 squared plus squared rho c sigma squared, where this is now a d-dimensional hyperbolic manifold.
Euclidean, totally Euclidean.
Yeah, so just a Euclidean solution. It's a Euclidean cylinder, like higher dimensional version. And so for instance, the thing that we have here, the cross section, is just this sigma, some hyperbolic manifold. So for instance, you could have, say, a genus 2 surface. You can put a hyperbolic metric on a genus 2 surface, and there's a connected wormhole of this type that you can construct. These type of solutions were constructed by Mardasena and Maus.
And that's the I shouldn't internalize the case, but if some specific theory.
Yeah, so this was so let me just start by saying, just in some, it's a very generic thing. You need so this on its own can exist just in pure Einstein gravity. There's no problem with it.
With a negative cosmological constant?
With a negative cosmological constant too, so that it's hyperbolic. Yes. But then there's various generalizations of this. You can add matter to it, you can add Maxwell fields, etc. And there's a whole class of solutions that exist. So it's pretty generic. It's not very fine-tuned.
So it's a little like a hyperbolic slicing of it.
It's exactly that. So the way they thought about this was basically start with the Euclidean ball, think about some hyperbolic slicing of AdS, and then do some quotient. So the quotient gives you some small part of this, and then it's basically, it's going to be some part.
And for this reason, you cannot make it with a torus, because you cannot put
yes, exactly. So that's why genus 2 was important here. You do higher genus and so on. You can make it with a torus if you add matter. So yeah. So there's a nice in AdS 3, these things have been constructed in great detail using these idea of quotients, and it's been nicely reviewed recently in this paper by Van Ramsdonk and Villar-Lopez. So you can look at this if you like. These are very concrete constructions in AdS 3 of solutions of this type, where you either have some higher genus Riemann surface and or matter on these surfaces, and then there's some cylinder-like geometry that connects this.
Just to sorry, make sure. So this is all in purely Euclidean signature.
This is purely Euclidean signature.
Sometimes there's a discussion about instabilities and
yeah, we'll talk about
okay. Sorry, and the motivation of Maldacen and Mao
Yes.
was the same thing?
Was the same thing. I mean, really, I hadn't appreciated this, but really the same sort of questions were asked. This is a paper from 2004, it's 20 years back, and you can almost ask the same questions that we're asking now, and we haven't made too much progress on it. That's
sorry, chronologically, just to say, Witten asked this question, right?
Yeah, so
actually,
before
it's from Witten.
Yeah, so before this, there's a paper in 99 by Witten and Yao,
Yeah.
where they wanted to say somehow that this never happens.
Yeah.
What they basically said was if you have positive curvature on the boundary, so this negatively curved genus 2 is not an allowed thing there.
Yeah.
Then they essentially proved that you cannot have such connected things in Einstein gravity.
Right.
And they took this as evidence that, oh, the AdS CFT correspondence makes sense, and here's the reason these things are not allowed.
Yeah.
But since then, we know that there's so many different constructions of it. So that was in a very limited setting. If you just enlarge your setting a little bit, then you find.
But nobody woke up. I read that paper. I didn't think about it.
Yeah, I mean, it's kind of remarkable. Actually, I will say that this Maldacen and Mao's paper was easily ahead of its time. Like, I think Juan understood these things way better. Like, a lot of these questions, in a way, this paper that we wrote is almost trivial. Like, I mean, whatever Juan said, like, it's a very small update on that. But clearly, the community hadn't appreciated it. I mean, it was obvious to Juan, but it wasn't obvious to everyone else. And so I think it was useful to just...
and maybe even to Juan, it may not have been clear how consequential.
Right. So I think people thought of this as a sort of separate problem as the information problem. And I think what helped was to connect them. That was but really everything was there. Good. So in this nice paper in AdS 3, you can nicely characterize the volume of space that you can fill in here. So other than having this genus 2, you could have, for example, say a sphere with some conical defects in AdS 3. And that's another allowed thing that would give you some nice solution. It will have matter insert. I mean, since there's matter insertions here, there'll be conical defects going all the way from one boundary to the other. Those are just sources that you've added. It's still the same factorization puzzle still holds there. It's just some insertions on this boundary which go up all the way. But nevertheless, this is still some partition function in the CFT. This is some partition function. They're both numbers. And so it's same problem.
One more comment. I sort of remember at the time thinking this was felt like a negative. It's like a problem. And problems are never fun to think of.
Right. I mean,
It'll go away at some point.
Right.
It's exactly something. Went away for winter and it'll go away.
It's exactly. Yeah. And I'll tell you why you may have thought this will go away, and it's related to this paper and some other stuff.
Sorry, why can't you construct a map? There was another reason.
You can construct with the torus as well. Oh, but not just with the torus. Like with no insertions, it won't work because you can't put a hyperbolic metric on it.
Okay. So you want, where do you point at hyperbolic?
I'm just saying this is one way to construct such solutions. You choose d rho squared plus cos squared rho with d sigma squared being a d-dimensional hyperbolic. That gives you a d plus 1 dimensional hyperbolic metric. That's a way to construct a d plus 1 dimensional hyperbolic wormhole. There's other things you could potentially do. This is just one construction.
Sorry to divert you, but I mean the other funny, if you take the n equals 4 theory and you put it on a negative curve,
we talk about
minus m squared, right?
Yeah.
And so you say, oh, there's something, but of course there's an identification. It's a compact space.
Yeah.
But it looks kind of a little weird. I'm just saying.
For the scalar.
Because they'll run off to some edge or something, you know.
But in free space, so just run off correct.
Identification is very interesting.
So this construction was not possible in the following limited sense. If you have a sphere on one boundary and a sphere on one and you have pure Einstein gravity, then there's no cylinder connecting of that sphere to a sphere with a solution. That was the thing they proved. Here, of course, we're getting around it because it's not, I mean, it's a negatively curved thing, the genus 2. Or we add matter, in which case it's not just pure Einstein gravity. Good. So and there's a nice way in AdS3 to characterize the size of the universe that we're obtaining this way. So you just keep that in mind. And that's the following. The volume of this space in AdS units is given by 4gm minus chi. M is the amount of mass you've introduced in the universe, so all of these conical defects and so on that we introduced. And chi is the Euler character. So you can write this as
this is
plus mu t minus mu. So for any genus higher, I mean anything genus 2 or higher, you have some non-trivial volume even without any mass. But you can of course add mass as well and make the universe as big as you like. Sorry? The total deficit angle? Yeah, I mean, each mass will come with some deficit angle. Yeah, there's a relation between the mass and the deficit angle, yes.
So we're now into...
This is a specific thing to AdS3. But roughly speaking, morally it's the same thing, which is that if you have large amount of mass, you can make this universe as big as you like. That's the mean.
Sorry, I didn't understand. What does mass mean?
So we're adding all of these conical defects, right? So there's some mass with it. So I'm just saying that there's different things we could do. We could add a genus or mass, and we can tune those parameters to make this volume as big as we like.
Sorry, the volumes of the throat
of this Cauchy slice. Yeah.
There's some reason, even without the masses, this has a finite size, right? Or not?
Even without the mass, I mean, if I take a genus 2, for example, then this has some finite size, which is AdS-ish size.
Yeah, so I don't need to buy it.
I don't need to buy it. I'm just saying that it can be made arbitrarily big. Like, because sometimes people might complain, oh, maybe it's a small enough thing, like, you know, effective field theory can break down, etc. I'm just saying this is like arbitrarily low curvature and big.
But anyway, AdS scale was arbitrarily.
It is true. I mean, yeah. It's just to make it even bigger. Yeah. It's like a bag of coal type thing. You can make the interior as big as you like, and, yeah, even though it was already big. That's right. Good. So, and there's been a lot of updates on these kind of solutions. There's a very nice paper by Marolf and Santos who constructed such solutions. And actually, their paper is interesting in that what they do is they construct these solutions in Einstein plus Maxwell and like a whole variety of these things and test in great detail whether there are any negative modes and so on, and you can test very accurately that these are the dominant solution and so on. And they construct a whole host of such solutions. So this is a very
and they're stable. In other words, there are even you said no negative.
So there's two things we can say about this. There's two ways you can think about it. One is from a slightly bottom-up type perspective, and separately there's a top. We can look at it in top-down models. So one of the issues that was originally pointed out in this Marolf and Maus paper, as you were saying, is this fact that sometimes these things with negative curvature have these instabilities. So CFT defined on a negatively curved manifold can have an instability. They tried to get around that, etc. But yeah, you need to be careful about these brane nucleation instabilities in the bulk, which are corresponding to those sort of instabilities. And many of the solutions that Marolf and Maus found had this brane nucleation instability, meaning that there was a chance that there was a better action solution which was actually disconnected, and so this is not the dominant solution. So it was not completely clear. So in fact, I would say the status even today is that there isn't a very sharp top-down construction where we're 100% sure that this is a dominant wormhole with no brane nucleation instability. However, what Marolf and Santos did was construct this whole host of solutions, and even Marolf and Maus did, in this bottom-up fashion, where the question really becomes, can you find a top-down model that contains that thing? But nevertheless, when they tried to have precise top-down models, which are some limited set of things we can access, in those things, they did find that there was some brane nucleation instability, and they didn't know what the exact solution is that it goes to. Eventually, what's the thing that dominates?
Is this instability worse in higher than 3 dimension? I'm saying that from the point of view of the field theory, it's an R phi square coupling. Now, at least is the if we take SD minus 1 times time, R in the case of a 2-dimensional theory, R is an S1. So there's no R.
Right.
So there. The fact that it was 1-dimensional made the problem made it. In normal situation, makes today your CFT worse. CFT is worse. And this is why you have these long strings. Whereas in normal situations, high dimensional CFTs are very stable with the positive coupling because you never have the end of long string. I was wondering if the inverse would also be that you'd find it easier to find sensible things in 2+1.
That could be. I think their analysis was largely in higher dimensions.
Yeah.
I'm
N
not
equals 4 sounds hard to make this, right? Because the fields, just from field theory, as Sandeep was saying, the fields look like the compound.
Yeah, I mean, what people have tried to do is then deform that theory with some mass terms, etc. I mean, this is what Madison and Maus tried to do. But I mean,
some flux and all, like Polchinski structure, some slowing.
Yeah, like do some extra quotient, like remove some degrees of freedom. A lot of things have been tried, but I don't think there's a clean case where I'm 100% sure that it works.
But in 2+1 dimensions, maybe it's easy.
Yeah, so Madison and Maus tried it in 2+1 and still found, when you look at the details, so there's no brain nucleation instability near the boundary, but there ends up being one close to the center of the wormhole. At least, I mean, they did this numerically and found something like that. However, they had proposed, it was roughly where, I mean, from the top-down theory, you get some effective parameters in your low energy theory. And for a certain choice of parameter, they could have found no brain nucleation instability, but the model where they tried to stabilize this theory, etc., that model didn't satisfy this condition that they needed. So even though in principle maybe some top-down theory could have given you that, the thing they constructed didn't give us that. So because of that, we don't have a sharp version where it works.
What is the statement of this brain nucleation?
It's basically like you imagine you have this solution. So when you have such a solution, what do you want to do to test it? You want to test that it's a valid saddle, which is dominant. So it's a really global minima of this action. So you can test for negative modes, firstly, just at the level of linearization, like it just in the low energy theory, you can look for modes which can decrease the action further. If that can be done, then there'll be some instability of this solution. It's not a minima, it's going to be like a saddle point, and then you can drop the action further and find something else. So that's the thing that's easier to test for. The harder thing to test for is in top-down models, you can have these brain nucleation instabilities, which is you can basically create some brain. So for example, pair create a brain which can split the work. Right? So you can have some disconnected solution where you have a geometry which ends on a brain and another geometry which ends on a brain. That sort of thing is what you want to compare with. And that is advantageous. So it's like pair production, right? So if you have sufficient electric field, there is advantages to create an electron-positron pair. It's like that. You basically test for that sort of thing where is it advantageous to add a brain? Does that decrease the action? In which case, then there'll be brains which will populate there and split the universe. So that sort of thing is what you want to test for to see whether this is a valid contribution in a top-down model where, I mean, that just makes the puzzle sharper, right?
And just to say, this is exactly the same thing that Sandeep pointed out, right? Because in the thing that Sandeep pointed out was that phi wants to blow up. The phi is, roughly speaking, the position of one of the brains.
So, yeah.
So, exactly the thing that you should worry about.
Yeah. And there are other proposals for such wormholes in top-down theories, like these axion wormholes, which have been computed. So it has a long history. These were, originally, I think, discussed by Giddings and Strominger, and then in the context of AdS CFT, discussed by Polchinski, Arkani, Hamed, and someone else. But anyway, the history of axion wormholes. So axion wormholes could potentially have been a situation where there's a top-down construction which actually can be shown to be dominant, etc. But axion wormholes have a separate problem, which is that there's been a controversy over whether these are included in the path integral or not. You have to be very precise about what is the contour for the gravitational path integral, and do these contribute to them? Because there's these funny things you have to do with axion wormholes where you have a wrong sign kinetic term and so on. So there's things to worry about there. And For that, you need a
whether you work in terms of the axion or its dual variant.
yeah. So the whole
Now worms coming back.
Exactly. And that is something that's debated till date. So
if it's important, I don't know what an axion wormhole is.
Honestly, I don't know in a lot of detail either.
But it's like you have an axion which is some scalar field, but you can have a kind of global charge for it, and then you hope that stabilizes them. I mean, it's just some solution of scalar coupled to gravity, but it's a bit subtle, whether it's the scalar or the dual three form in 4D, etc.
And what makes it an axion?
Just a word with
I think it's a super scalar, right? Like, in that sense.
I don't think they're so sensitive to the breaking of parity and their wormhole constructing, so it is kind of.
Yeah.
That was the original paper of getting this from.
I've not delved too deeply into that history, but there's been a lot of discussion around it, and I would say it's still controversial. So that's potentially one top-down construction which would have given us such a situation. And this is what Polchinski et al. Claim.
But you wrote a paper with Nima.
Yeah, that's right. That paper basically talked about axion wormhole. So it was a follow-up to Mandelsena Maus in some sense, and that talked about axion wormholes as the example where this works and it's top-down, stable, etc. They never bothered. I mean, they had some words for. You have to worry about whether these things should be included because you have to first define the contour for the gravitational path integral, which itself is a complicated mess. And so once you have a proposal, you can test. Now, there are different proposals for what the contour for the gravitational path integral should be. Don Marolf, for example, has recently proposed one such proposal under which they find that axion wormholes don't contribute in higher dimensions. So it really, it's a sensitive question, like what choice of contour.
It seems like an interesting question in this.
But irrespective of whether these saddle points exist or not, one would have thought that such topology should be included in the gravitational path.
Right. So there's a question of whether if it was possible. So suppose you had solved the factorization problem in some way where there was this contribution, but there were some other contributions as well, which somehow cancel the effect of this and so on, such that it in the end factorizes. Well, then you might as well have just said, don't include them. Like, what's really the difference between including such topologies or not including them? So they're only making a dent if they're different from the factorized answer. And that's what we're trying to understand. For this fact, by the way, it's not so important that this is dominant. This is true even if this is a sublead. This is an issue even if it's a subleading contribution. It's going to be important that it's dominant for what I'm going to say afterwards.
I mean, it's certainly subleading in the topology counting parameter, right? Because each of the single expectations go like a higher power of, let's say, e to the s.
Right. So, but you can have situations like a simple example is in JT gravity, where let's say you can have a 1-point function with a single operator, a circle with a single operator. This has a 0 1-point function. So the connected piece is just vanishing. And the only thing that contributes is the cylinder, which has, so there could be situations where in topology counting, yes, but it can be suppressed. Okay. So very good. And the last thing to say about this is there's one geometry which we're reasonably sure is stable to everything that we know, like linearization, brane instability, etc. And that's the double cone geometry of Saar-Shaker-Stanford. The double cone geometry, what they do is basically take black hole geometry and look at a section of it with some time t. Take 2 of these copies.
This is Lorentzian.
And just identify them. So this is this double cone. So this is one cone, this is another cone. Which are connected. You have to slightly go into the complex plane to smooth out this seeming singularity, but it can be made sense of. This is a geometry that contributes to the calculation of trace e to the minus IHT times trace e to the IHT at fixed energy. So at fixed energy, you can compute this trace. It's in some microcanonical window. We're computing this spectral form factor. And this is a geometry that contributes to this. So this has a Lorentzian closed time-like curve of size t on both sides, and there's a connected geometry between them. So it's much like this, if I just draw it in the other way, it's just like this cylinder, but it's connecting 2 different boundaries. This thing, of course, these things should factorize in a given CFT. And the picture you should have in mind is that in any given CFT, the form of this quantity looks like the following. It decays for a while. then it sort of starts fluctuating, it grows like a ramp, and then it stabilizes, but it has all of these fluctuations that stay forever. That's what happens in a single theory. This double cone doesn't reproduce that answer. What it does reproduce is sort of the envelope, the smooth envelope of this, which is the curve that looks like the mean of this thing. So it sort of washes out all these erratic fluctuations and gives you this smooth ramp and plateau structure. So clearly in this stage itself, we know that even though this is stable to all bulk processes, it's still questionable in the sense that if we really believe that the gravitational path integral should be, or like with extra ingredients, should be able to reproduce the answer that you get from a single CFT, then of course we're missing something. We're missing some ingredients which would have given you these erratic fluctuations. So presumably this also gets important corrections from those. The important thing is we don't know what those things are. These are what have been called half wormholes, but we don't really know what a bulk picture of these things is. But if you believe that there's a bulk description, a bulk path integral, which reproduces the answer from n equals 4, there must exist some ingredients which would give you that answer.
How big the window can be?
This time window? It's this thing only dominates when this time window is taken to be exponentially large. So this ramp time is roughly like e to the s black hole. It can be made polynomial in S. In the microcanonical ensemble, I think it can be made polynomial in S. So I think it's polynomial in the S plan.
So the fact that your geometry has closed timeline curves is not a problem.
It's not a problem because the quantity you were computing on the CFT had closed timeline curves.
But people used to say, at least in the old days, that gravitational solutions with closed timeline curves would be, we generate infinite energy because things will go around.
Oh, but we're projecting onto fixed energy, so you can't arbitrarily do that. I mean, there's a bound on how much energy you can have because of the fixed energy boundary condition. Maybe you're worried about like the one loop determinant on
that kind of thing. That kind of people used to say that would go.
Yeah, this thing satisfies the Savage-Seagal criterion, which is supposed to be like what tells you whether the one loop determinant is finite. I mean, at that level, it's fine.
But the concept of Seagal is a local criterion.
It's a local criterion.
The worry was the global effects will we don't need to detail.
Yeah.
It's just that the rules used to be that anything with closed timeline curves is bad.
No, you were talking about this double cone, right?
Yeah.
Yeah, I had a similar question that, I mean, when the geometry was first introduced, I really thought it was a bit crazy for this reason.
Yeah.
But a lot of people now say it's okay. And after slight complexifying, it meets whatever KS, whatever criteria there is.
Yeah, that satisfies the Savage-Seagal criterion.
But I think it's relevant to me because
Can you explain about the
Seagal is a point-by-point condition.
I see. What is the condition?
It's the condition that you roughly have just one time-like direction, not more than one time-like direction.
In that every time, kinetic term on your contour is positive definite. Okay, but the worry always was that things will build up. So it's not point by point.
Okay, so that objection, these have.
Well, what exactly do you mean by build up? Actually, can you explain?
It was never very clear to me, but the idea was that there would be a sort of resonance, that something starts here, goes back, comes back, builds up.
Some amplification.
Yeah.
This chronology protection conjecture, the chronology of Hawking, etc., that Kip Thorne also worked on.
Yes.
It was just based on this, that, for example, if you compute this quantum stress tensor, for example, with closed timeline curves, you get divergences because, you just go around and build up. Okay, that was the thing.
Yeah, people used to say these words.
Yeah, I don't know to what extent.
I'm confused because this is a quantity I can compute on the boundary theory. And you could have said the same things about the boundary theory itself. That has a closed timeline curve. Computing some CFT quantity on that. But this is manifestly finite. Like this is just some over discrete things. It's like just you can put a bound on it.
When you make this identification, because the lines go all the way to the boundary.
Yes.
We are making it that closed timeline curve for the boundary.
Yeah, on the boundary, we're computing trace e to the IHT, which you should think of as starting at some time, going forward in time, and then identify, because it's a trace, you're identifying it. So it is indeed a closed timeline curve on the boundary as well. But this quantity is just finite on the boundary.
You put the energy.
With an energy cutoff, with an energy. I mean, even if I computed this in the canonical ensemble with some finite beta, it's still finite.
Sure.
So that's another thing. Yeah.
You don't have that.
But you can still complain about, yeah, exactly.
Yeah, and does it blow up as beta goes, as the imaginary part of beta goes to 0?
That's right. Yeah, because then you have access to infinite energies.
But the phase cancellation doesn't save it.
No. I don't
Okay, so that would have been the version of that problem.
So you could say that.
Yeah, because
But this quantity is okay. So maybe the point is at fixed energy it's not a problem, but if you have all energies, then it's a problem.
and how do you do the project to fixed energy in the
So here in the bulk, you're just imposing a fixed boundary condition, which is fixed
On the
energy
boundary.
on the boundary. Yeah, it's on the boundary.
so maybe that's the point. That
Yeah.
you can
I mean, I
project
guess,
away the problem.
I guess roughly what would happen is if I didn't fix the energy, then you would have access to arbitrarily high energy black holes, right? So there would be similar cones I could draw for higher and higher energy black holes. They'll contribute more and more, and so it will be dominated by that thing. But here we're projecting onto this fixed energy of not.
See, so somehow you project to the fixed energy, and then because you're doing a trace, you have a closed time-like curve, but the fixed energy
Once you
protects you.
Once you've got a projection onto a fixed energy, any trace is bounded
It's going to
by
be
the number
finite.
of
Yeah,
states.
exactly. Exactly.
So what can go?
What can go?
Exactly. Yeah.
Antonini, can you repeat shortly what was the statement of that graph? What you want to say on it?
Of this graph. So what I'm saying is the erratic behavior is the thing you would get in a true series. So in say n equals 4, if I computed this like using a computer, this is what you would get.
What is the graph?
Oh, sorry. It's this quantity. So this quantity is the y-axis, and this is a function of time.
So it's clear that it makes sense of the
Sorry, I should have said that. Yeah. So this quantity is vector form as a function of time. Looks like this. It decays for a while, then it stabilizes and it has this ramp plateau behavior, but there's like wild oscillations around that. So in any given theory, what the double cone gives you is not that, it gives you the smoothed out version of this. So now the point is, suppose we in a putative bulk theory corresponding to n equals 4, you may ask how do we compute this quantity, and if we can, it must be that it doesn't give us the smooth answer, it gives us this wild erratic answer, and whatever those effects would be big corrections to this double cone, right? Because it's like wildly changing the answer to that. So it's still some putative instability which we don't understand. Like we don't understand what that bulk thing is, but there must be some correction to that if there's really a top-down version of that.
Just a quick comment. The eta function is an example of this in field theory. Right? The eta function is nice, well-behaved analytic function of the upper half. Right? That's why you have positive Euclidean suppression. But when you go to the real axis, it's a completely untamed beast because it has a singularity in every direction. So this is an example of this being a nice analytic function for positive suppression.
Right.
But you come down, you try to make sense of this really in Euclidean time, and it completely blows up.
Right.
Really in Minkowski. I see.
Yeah. So I guess that's
There's one kind that goes on. If you try to make it a torus partition function in Lorentzian time, you just see because it's a very simple function. You can look at it.
Yeah.
Mathematicians have studied it forever.
Yeah.
And it's a very crazy function of that on the x-axis.
Yeah. Yes. That makes sense. I mean, yeah, instead of this, if we compute something like z of beta plus it, z of beta minus it, then you're saying like in the limit where I take beta to 0, then it's a 1.
I said beta is completely crazy.
Yeah, then that makes sense. Here you're saved by the energy.
So where is the information about the capital T in the graph?
Capital T is small t. The same thing. There's one time. There's one time we're choosing for like trace of e to the IHT with that time on the boundary. That means that we have a closed time like curve where we start with of length t. With that's identified at t. That's computing this quantity, which is depends on time, and as a function of time, it looks like that.
And one more thing, how do you know that the bulk thing is this double cone?
I don't. This was just. I mean, the Sath Shankar Stanford found this geometry and saw that it contributes. It dominates over the naive disconnected answer, and the answer you find from it is this smooth version of it. That's the level. This is the only geometry we know which gives us anything remotely close to that random plateau. That's what. I mean, in gravity, you're never sure that the thing you have is the right solution. It's just you propose something and you check.
But if you, just from the boundary perspective, can't we read off what the bulk contribution should be?
How does it? We can read off the number. We can read off the plot. We can read off that the plot looks like this erratic function. Then there's a question of how do you get that answer from the bulk. It's like the page curve. Like for the page curve, we could have always computed it in n equals 4, right? And you get some curve. The question is how do you get that from the bulk? And we only learned recently how you could possibly get that from the bulk. So it's not always trivial that if I know how to calculate it on the boundary, I can calculate it in the bulk. The black hole S matrix is an example. We know how to calculate it on the boundary, but we don't know how to calculate it.
Just a quick clarification. Does this geometry also give the plateau or just the?
It can give the plateau. You have to be a little careful about the plateau. But morally, yes, it gives the plateau.
And Pratik, you must go on, of course, but the scale of the fluctuations on the broad end is that in n equals 4, that would be some 1 over n square effect, right? Not e to the minus n, right? What do you think?
The scale of these fluctuations?
Yeah.
No, it's an e to the.
It is an e to the
It's an exponential.
So then it could be that there's some very high energy physics in the bulk, exponentially suppressed, which that the low energy gravitational theory just produces the envelope, but it's really non-perturbative e to the minus 1 over.
But whatever it is,
Spacing between two states. That's
yeah,
what
it's going to be dominated by spacing.
Okay, spacing. Yeah, that's the way.
So it's a very finite n thing.
It's a very finite end.
But whatever it is, the point is whatever that UV physics is, it must be such that it spoils this to a large enough degree that the curve changes significantly. We don't know what that is.
Just add some corrections.
It's not a small correction. The value here is comparable to the variance. Like the oscillations are really bad. Like maybe I screwed it badly. That's what it is.
That's what it is. Okay, sorry. I see.
It's not small at all. And you can check that it's not small because there's a version of this where you compute. So here what we're really computing is this thing, right? And instead we can compute this quantity squared and average it, compute the variance, and we see that it's big. We see that it's comparable to the mean.
This geometry is not like that for me.
It is like that, roughly. Only difference here is the Lorentzian part.
The volume is equal.
Yeah, so in that sense, it's not. The volume is pretty big everywhere else. There is some regulation you need to do here to get like a finite volume, but yes. So it's not literally that. I'm just saying this is a connected contribution. Since we were talking about top-down versus bottom-up, this is a connected contribution where we don't know any possible way that this is this way. It's stable to everything that we have tested.
But just a side question, how does the graph look like if the geometry is disconnected?
It's just the decay part, so it just decays forever. It just goes to zero. That it's related to this Maldaceno's version of the information paradox. If you compute the 2-point function, you see this decay forever, and there should be something that stabilizes it at some value, and this is similar to that. With the disconnected thing, you just see the decay. Very good. Okay, so good. So that's the status of this stuff. So now let me talk about using this to somehow connect it to the black hole information paradox. And the way we're going to try to do that is take some of these solutions and essentially try to interpret them as states in the CFT. And the way to do it is, morally speaking, just cut open some holes here and connect them by tubes, by thin tubes. So that now we can cut it open in the middle and we have some state living in the CFT which still has a closed universe on that same slide.
Please say again, what is the motivation you're trying to do?
What I'm trying to do is try to connect these paradoxes. So what we discussed here is the factorization problem about closed universes, which a priori is not very sharply connected to the black hole information paradox. And what we're going to try to do is somehow think of a tunable parameter which takes us from one to the other.
These tubes can go through the bulk vessel, right?
They are going through the bulk.
But you have drawn it
Through the let me draw a separate picture where we can see exactly what this looks like, and then we can. I hope that will answer. So let me consider a concrete geometry where we can write this, and but whatever I said here holds. Like we can always connect any of these solutions with these tubes and get something of the kind. So here's this thing that's called the AS squared geometry. It's Antonini, Swingle, Sasieta. And it's pretty simple to visualize in AdS3. So let's think about a CFT2, where what I'm computing is torus partition function. But I'm going to draw it in these two parts. So it's a torus partition function where there's an operator inserted. So we have an operator insertion here. these surfaces are identified. So there's just one operator insertion.
The operator, you mean state,
No, I want to think of it as a heavy operator that I've inserted.
but not a local one. You've drawn.
Yeah, so here I'm thinking of it as a shell, like a spherically symmetric operator. You can think of it as a product of many operators, if you like.
And it's on both those viewing regions.
So this is in the bra, this is in the cat, and these are the same. These are identified. So I'm just drawing a torus. It's still a torus. It's just it just has these marked circles. It's going to be useful to draw that. So we can now think of these separately. Separately, and we're going to consider beta. So this is going to be what I call beta over 2. This is beta r over 2. And we're going to take beta to be large. So we're going to think about this in a regime where beta is large, where we expect that the dominant solution is the thermal AdS solution. So if we didn't have this operator insertion, the natural solution would be that dominance is the thermal AdS solution. So we would fill in these this torus along. I mean, this thing would be the contractible cycle. So if we fill it in that way, then in this whole part we expect thermal AdS. We expect thermal AdS.
Which one are we filling in? Sorry,
This circle, like this circle.
that's how it's becoming solid.
Yeah. So the picture for this, for what happens once I've added the operator, is we would have had a whole tube of worth of thermal AdS, but now we can draw some part of it. So this thing has some stress energy tensor, follows some path, which looks something like this. Okay. So this thing would have been a thicker tube with full thermal AdS, from which I've sort of shaved out the outer region and marked out the interior of some large radius where this world tube lives.
Wait, just in field theory, you need some boundary conditions on your two circles to define
so
that.
this boundary condition is some source. There's some source I'm adding there. This source will be a source of stress energy for the bulk.
You think of it as some complicated.
Some
State. So I think
you can say state.
state sounds clearer to me because it's a boundary condition or a path attack.
So if you had only one of those,
Yeah.
then it would be a state.
Yeah, I have
And
two of them.
identifying the features of it, then it becomes a norm.
I mean, this path integral is just this, right? Like it's just
She's identifying state.
Those having the same state on the two sides.
No, not
you can say that, but I mean, it's just this operator that's inserted. It's just this operator that's inserted in the torus partition.
But if just one at a time, I just want to understand the path integral.
On the
Just
CFT, right?
CFT, yeah.
So that maybe this picture is more useful for that.
Uh-huh.
It's just a torus with this circle marked with some.
Oh, you don't say what it is, you just say that it's identified. Yeah, so
If we can think of it as just one operator that I'm adding there. Like, forget about these two pictures. It's not useful for the boundary picture. For the boundary picture, we can just think about the torus, and on these two rings, I've added some operators.
Okay, fine.
That's the boundary picture.
Fine.
It's going to be useful to split them here to see what the bulk is.
Yeah, so now tell me, in the split picture, can you say that in CFT language?
In CFT language, I think you would say what you said. Like, you have some boundary condition, which is some state, and then you glue them by saying it's the same. Same, yeah.
It's not exactly this.
I mean, one way to think about that would be like, there's some state you've prepared on this side, and then
There's a matrix element.
I would say that either you can think of the one-sided case or the two-sided case. The one-sided case, I would just draw half of this picture.
yeah,
Right.
this picture.
And then there's a state.
That's a
state. Or you can think of the two-sided case where there's an operator insertion. There is two different ways.
No, but one-sided case, the
Yeah.
fact that you have the bra and cat, are you thinking of it as two boundaries?
One boundary condition here, another boundary condition.
Yeah, it's the same.
Past and future?
Yeah.
Euclidean.
But
Yeah.
Euclidean Boston picture.
Okay, everything Euclidean.
Everything.
Euclidean.
In the boundary theory. of it.
In the boundary theory also.
Okay, great, thank you.
So this is some operator I can call O. It's the same O diagonal.
Sure.
So you have a Euclidean boundary and the left diagram is so disconnected. Is what? What is that? I just make sure.
No, one-sided case seems very clear.
Yeah, the one-sided case is just this thing.
It's just there, and then you put one state there, another state there, because you've got, if you end the path integral, you need a boundary.
Yeah.
Okay, that's all it is.
That's all, yeah.
Okay, fine.
So, and whatever the boundary condition is, however you say it, is some state, right? The one-sided case is very clear. And if two-sided, it sounds to me like because you've got an operator, you're relating the boundary condition here to the boundary condition there through a matrix element.
That's good. That's good.
Yeah, I think,
And so you can say it that way.
I think you could say that way.
And then you can sum over all boundary conditions
Yes.
with the relationship.
Yes.
That's the effective example.
Yeah.
That's what that
Yes.
operator.
Yeah.
is.
Yeah.
Okay.
And here now we're going to identify everything. So everything here is identified here. So now we can think about what the state is living on the time symmetric slice.
Is it going to be important to be two-sided? If it was one-sided, it's easier for me to think of. So.
Okay, I think it's not going to be important. I mean, I think it's not going to be important. I think it's fine if it's.
Universe to the one-sided case as well.
Yeah. I think everything can be said in the one side. Yes.
So
Maybe
you
we
say
can-
carry on, I'm thinking.
Yeah, that's good. I think it's not going to be important for anything. Yeah. Sorry. Yeah. So these blue lines are, so we have some source of stress energy tensor here, right? So this is, should think of it as roughly like some pressureless dust, some particles that have been inserted. And those things are going through the bulk. This thing would have otherwise been thermal AdS. And this blue line is some trajectory in thermal AdS. Right? And there's some region inside that's filled in by the thermal AdS solution. This is some trajectory that's followed there. And these are identified with each other. So you need to check the Israel junction condition when you glue them together. And there's a jump in extrinsic curvature, but that jump in extrinsic curvature is satisfied by the presence of the stress energy tensor for this pressureless dust. That's what that solution is.
But now, is it the case that upstairs is two disconnected Euclidean boundaries?
No, they're connected. This is identified everywhere. There's an identification all the way. So the boundary looks like that. The boundary really looks like that. The only thing is when it's filled in, there's something here, there's something here, but there's also something here. There's a universe there.
So where is the boundary of the
Where's the?
boundary of the radius?
This is the boundary of the thermal radius. Like the white stuff here. This gets filled in with thermal radius.
And the shell is inside the
Yeah, so imagine if you didn't have the shell. So suppose I didn't have any stress energy tensor here and I just filled this with the remaining torus. I would have just had thermal AdS. Now I'm sort of shaving off that boundary. So I would have had an asymptotic boundary in this region. I shave off everything outside a particular radius circle, right? The trajectory of this would be shell. Now there's no asymptotic boundary left here either. This is a finite region inside some radius. And then I'm just gluing that onto another copy of it.
Sorry, what is Brian get here? Is it
Bra is the top and get is the bottom.
and what are these two things? Can you explain again?
I mean, in this case, like if I just have the torus, I just had torus without any insertion, then here, one way to think about it is a thermofield double, right? Like the thermofield double is a two-sided state prepared on these two circles. So there's a circle here and a circle here, right? With this being the ket and that being the bra, and we're computing the overlap. This is the same. It's just there's an extra operator insertion there. It's the same thing. It's just a slightly deformed thermofield double.
So just to understand in your above diagram, the two white lines there are indeed asymptotic boundaries.
Yes, the white lines are all asymptotic boundaries.
And then the blue stuff is
The blue stuff is a bulk geometry, which is finite.
So it's
But
a
this is a bulk
multiple connected
geometry.
kind of bulk geometry.
Yeah, there's a bulk geometry here as well. So this whole thing is filled in with thermal AdS. This whole thing is filled in with thermal AdS. This whole thing would have been filled with thermal AdS, except we've cut out some parts and then glued the interiors to each other.
So it's like some multiple connected bulk or something. I don't know if it's quite that, but you have this solid region, you have that solid region.
Yeah, there's three solid regions. There's
Yeah,
this region,
three solid
region, and that
regions.
region. Okay, very good. So let's just write down what the state is. State. So let's say with these O's, I add some label I for this operator. So the state on the two. So now this is going to be a state on two CFTs or one CFT, and 1 over square C. E to the minus 1/2 beta L plus beta of beta L N plus beta.
Sorry, but in your two-sided case, you
Yes.
had identifications of those blue lines, right?
Just a second. Sorry.
So in your two-sided case,
Yes.
you have identifications. So then there's so those two blue tubes I should think of as being the same thing.
It's one blue tube. Like really, this picture is there's one universe. So if I just cut it open here, so let me just say that overall as well. When I cut it open on this time symmetric slice, there's obviously thermal AdS here and thermal AdS here. So that's the standard thing. The extra thing we have here looks like this. It's basically a disk with this blue line glued onto another disk with this blue line with these two identifiers. So there's really only one blue circle. There's disk on one side, and they're glued on that. So it's really like a sphere.
Actually.
The right dimension of the bulk dimension.
So here we're in AdS3, so it's literally a sphere.
Okay.
But you say that this tube is finite.
This tube is finite because it is. I mean, what we did was, so how was this disk constructed? So this disk you should think of as if I had thermal AdS, which was some big universe, where this is really an infinite boundary. We look at some sector of it, which ends at finite radius.
Why?
Well, let me just complete that. We take some finite region such that, so at this point, this will have some extrinsic curvature, right? And then I take 2 copies of this. And I'm gluing these two together, excising out this exterior region. The reason is when I do that, there's some extrinsic curvature here and there's some extrinsic curvature here. The jump in that extrinsic curvature is balanced by the presence of this matter. So you think about it this way, like as you start from the interior and you go outwards, the area is growing. Right? So if you think about it in the picture of the disk, you start from one end, the area is growing, you hit the shell. There's going to be a contraction because of the presence of the shell. And the area then starts shrinking and then pinches off at the other point. So the presence of that matter grows the universe and then shrinks it. It's not allowed to then keep growing in area. The presence of that matter is the thing that's bringing you back.
So we're not interested in the outside. I was going to say,
We're interested in the inside.
You're interested in the inside.
Yeah, we're filling this inside. Because there's no other asymptotic boundaries here. We're really looking at this boundary condition for the CFT. So there's nothing really here. The only thing that's allowed is some bulk stuff. There's no boundary there.
But you have those white lines which are.
These are there. These are always there. Those
That's
are
like
giving you asymptotic AdS universes.
That's what you would have had with thermal.
With thermal AdS.
But
This is an extra thing which wasn't there and there's no boundary corresponding to it.
there's no boundary corresponding. But I'm just saying that your sphere, which is this closed object, is lying. Is it to be thought of as lying embedded in the outside region?
We can talk about it. It's not geometrically. The geometry looks like this. So the geometry
disconnected.
It's disconnected.
The
geometry-
geometry disconnected.
Yeah. So geometry is like this. So there's, if I analytically continue to Lorentzian, there's an AdS universe. Let's call that AdS left. There's an AdS right. This is what you would have had without the insertion. So this is this part, that part. And then there's this region in the middle, which we can draw roughly like this. It's a sphere with some insertions on the equator, which then crunches in both past and future. It's a finite universe and it's AdS. With this negative cosmological constant, it crunches in both directions.
It's like a cosmology.
It's a cosmology. We should call it a closed cosmology.
There are these cosmologies in negative curvature space.
Yeah, this is basically an AdS cosmology, closed AdS cosmology.
And this satisfies Einstein's equation.
Yeah. The reason it does is, I mean, it satisfies Einstein equations.
You can make cosmologies that are sort of without singular stuff.
Yeah, you can make this much smoother. So as I was saying, like in this paper by Van Ramsdonk and Villar-Lopez, they construct a whole host of solutions. So instead of having one spherical shell, you can have many like diffuse dust, etc. It's just there's some amount of matter which makes this universe big, and that's sufficient. You could have also made it genus 2, etc. Like there's other things that work. Yeah, it didn't need to be singular.
I think we could have had photons.
We could have had photons.
Right? That's what we study as undergraduates.
Yeah.
You didn't need your extrinsic curvature to jump because of some shell meeting.
That's one thing that could happen, but if you have photons, then that's going to just happen slowly. It's going to happen progressively, and eventually it's going to close off the universe. So it's still going to satisfy the Einstein equations.
And so it's one of these spherical universes with negative cosmological constant that start at a Big Bang and end.
Yes.
What is this blue line? Does that indicate the upper line?
In this diagram, the blue line is the sort of bulk dual of the stress energy that we inserted on these green circles. So the green circles have some source on the boundary, and that's inserting some energy into the bulk. The trajectory of that energy is this blue line. It's just simpler to visualize. Otherwise, you could just think about some diffuse energy that's going from one side. Okay, good. So the state that we define is this psi I, which is just, I mean, this is how we're expressing it. We just have, we've written it as a superposition over these energy eigenstates with some operator matrix elements and this extra Euclidean evolution. Good.
And this operator is a light operator.
No, it's a heavy operator. It's important that it's a heavy operator. If it was just a light operator, it wouldn't be able to support this universe. It's important that it's heavy. It's somehow what's going to end up being the broad story is that it has to be something that somehow accesses the black hole spectrum. So it is heavy enough that on its own, without this extra Euclidean evolution, it would have formed a black hole.
Just to make 100% sure, if I just think of the Friedman-Robertson-Walker equation, there's something like if R is the scale factor, it's R dot square plus 1 K over R square equal to lambda plus T mu. So if you wanted K to be positive, you could not have done it without matter, right?
Yeah. If it's spherical, I guess. I mean, if you had genus 2 or something, maybe you could do it.
Okay.
Yeah.
But
yes, if you want a sphere, then yes.
Okay. And so therefore you would have the matter, or you would even just do it with genus 2, have a crunching universe, and get away with it without even any matter, just pure cosmology.
Yeah.
Okay. I see. All right.
Good. So that's the state. And so this is what we call description 1. So this thing is description 1, which is a description of this particular state. So this psi I is some CFT state in the tensor product of CFTs left and right, which has this particular description. It has some.
Why is the closed universe contained in the tensor product?
All we did here was it's standard AdS CFT rules. Like we just prepared this path integral on the boundary and cut it open. So that prepares some state on the CFT. When I cut it open here, it just prepares some CFT state here. And all we're doing is just using the standard rules of the path integral to see what is the bulk dual of that. The bulk dual is this geometry, and all I'm doing is cutting it open at this time symmetric size.
I'm so sorry, I didn't understand that. I mean, I thought it was some kind of contrived situation. What was the original CFT state? Or?
The original CFT state is this one, which we can think of as being defined by a half-torus partition function with an insertion of this circular operator.
And that's in this ONM.
That's this ONM. The ONM is that operator. So that operator plus some Euclidean time evolution. This prepares some CFT state on this tensor product. That's just this boundary CFT. Boundary CFT path integral.
When you cut it across.
It's just this thing, yeah. Without the bulk. Just that. And then we fill in the bulk and we find this solution, which has this closed universe.
In the path integral, this must be a subleading solution.
So in this case, yeah, so there's been a lot of debate around this. So as we discussed before, there are situations where you can have all these connected normal solutions which can be made dominant, at least in bottom-up models. And whenever that's the case, this will also be dominant. So similarly here, you need something. So it ends up being, it depends on the details of the operator. What we really used here is that this operator doesn't have a 1-point function. So it wasn't allowed to fuse with itself. Right. So one thing that could have happened, like if you imagine like a set of small particles or something, then they can just contract with each other so that they don't go from bra to ket.
It gives them charge.
So you have to give them charge, but the problem is you can't give them like standard gauge charge because a closed universe doesn't support charge. Like a closed universe needs to be chargeless. So you can't have gauge charge. It has to be some global charge. And that is the thing that has that. That's why it's not so sharp, because you need a clean. It's not as clean because, of course, we think global symmetries are broken, but then it becomes a question of how badly is it broken and can it be made in a way that it's not. But so that's why this is one example, and that's why I was trying to emphasize all of these other examples where we can construct all of these closed universe solutions. Those can be shown to be dominant. So, like for example, in these Einstein-Maxwell type theories, you can just construct them out of the Maxwell field without adding this spherical operator, etc. And they would be very similar. Just adding tubes to them, since those were dominant, these will also end up being dominant.
So this can be made to.
Yeah.
I'm really just trying to digest this thing. So
Yeah.
that was your initial state,
Yeah.
And then this whole geometry is just the inner product. Is that what?
Yeah, this is just computing the norm of this state. Or if I put an OJ here, it's computing psi Sij.
In an equals 4 context,
Yeah.
it's sort of important that your operators are built out of glue balls, not glue ones, right? So that you have a bulky description.
Yes.
Very, very complicated.
Yeah,
Yeah,
did you
yeah,
vary
yeah.
the
Connecting the two bonds.
no, but did you vary it and with lots of things in one place, or and not some crazy operator, right? The kind that causes stuff to go into the bulk, so that you get a bulk.
Yeah, anything that would have formed a black hole otherwise, like
Would have collapsed into black.
would have collapsed into a black
But
hole.
didn't start as that.
That's
Didn't start as a, but this is also that.
Yeah, lots of traces. Lots of traces meaning, but in the graviton Hilbert space.
In the graviton.
trace by x1, trace by x2.
Yeah.
Yeah.
Linear bisecting.
Yeah, anything that would have collapsed into a black hole, that sort of thing.
Okay.
As opposed to just one of these.
Already in fact.
Meaning, if you just count the number of states that would have collapsed into a black hole, that's e to the power n to the bar, some number smaller than 2. Because it's the Fock space of gravitons. Whereas the number of states that make up a black hole is much larger. So
That's
when you
what,
start with
that's what you mean.
this special set of states.
It's still a special set of states. Yeah.
Yeah, just because the number of states grows like e to the power 9 by 10.
Right.
Because for those smaller fraction, you have an explicit understanding.
Then you will make geometry when you. This part will become geometry.
Yeah,
Otherwise, it's
yeah.
some crazy stuff, right?
Right.
Black hole stuff.
Yeah, so already a black hole. It's not collapsing into a.
Right. Yeah, we want this to be some sort of diffuse dust or something like that, so that it has that. Okay, very good. So this is what we're calling description 1.
Yeah. Just trying to understand. So the way you initially described it was a Euclidean setup.
Yes. And then we cut it open, we define some initial data, that initial data is here, and then we use that to evolve into Lorentzian. Yeah. Okay, good. So here's where the puzzle comes. The puzzle is pretty straightforward. This is description 1. We just use the gravitational path integral to construct this solution. But of course, now what it's given us is, and just to emphasize, there's entanglement, right? So there's this is a connected Euclidean spacetime, even though the time symmetric slice is disconnected. The spacetime itself is connected, and so there's entanglement between them. So there's some entanglement between these universes, and also these universes.
So there's some shortening the time frame in a way that it does not intersect with loose.
Well, how?
Because,
Like I would have to cut from some other asymptotic boundary or something.
in the Lorentzian picture. The left picture you could
Yeah, here I could, but not here. I mean, I think what you're doing is taking this, going off in Lorentzian space, and then going above the singularity or something like that.
all these slices are disconnected anyway. So what do you even mean by this principle?
It's the time symmetric slicer. I mean, there's one Z2, this geometry is Z2 symmetric, and there's a time reflection symmetry slice. I'm looking at that
So I'm
slice.
saying you could have chosen time on the left
Yes.
CFT and right CFT.
Yes.
And you could have kind of slice.
Yeah. But, so that makes it confusing because of diff invariance. But I'm just saying, in this particular case, there's a clear moment of time reflection symmetry, both in the bulk and the boundary. And I'm just choosing the state on the boundary at the time of moment of time reflection symmetry and looking at that state in the bulk. I mean, the thing you said, you can say for any construction of a state in the using the gravitational path integral, right? There's always this ambiguity of which slice in the bulk and so on.
Yeah.
And so here, I mean, because there's a time symmetry, there's a clear good choice.
I mean, at least in the first lecture that you gave, it
Yeah.
was clear, right? You could have moved the universes anywhere, and then at a given slice,
Yeah.
you won't have said that just two different universes are entangled, right? Because you would have just moved the time state in a way that the slice does not intersect like one of the questions.
You mean
So when you were computing gravitational quantity of the some asymptotic boundary,
yes,
you were like trying slices.
Yes, yes,
You could have chosen the slice
yes.
in a way that it did not intersect any of like, let's say one of those UPs.
No, it's not always. I don't know what you mean. Like if I have something like a cylinder and I'm cutting it through anywhere in the middle, what slice do I draw which avoids that?
No, but if you have like let's say another cylinder, okay, you could have moved the second cylinder to the bottom.
No, but then you're crossing an asymptotic boundary. That's a different state.
Okay.
It's not, I mean, it's not obviously the same thing. Like we're defining some state by saying, here are the insertions we have in the Euclidean past, here are the insertions we have in the Euclidean future.
Okay, so you always have an option of Euclidean past.
I mean, at least a priori, yeah.
Because but then you said you could write the inner product between Euclidean past and Euclidean future as an expectation value and
Yes.
put on.
Yes, there is some commutativity there. It will change like whether you star this or not. So there's some, I mean, like for example, if this was not time symmetric, if it's time symmetric, I think it doesn't matter, as you're right. Like, but if this was, I mean, this was J1, J2, J3, J4, whatever, then the path integral you would compute here would be ZJ1, ZJ2, ZJ3 star, ZJ4 star. If you cross it down, then the interpretation is the opposite. But now it's in the K, so there's no star, for example. So it does make a difference whether it's below or above. But anyway, in this case, like we're really using the time reflection symmetry as a clear bulk slice that has that time reflection symmetry.
And so I guess the new feature here, of course, if you just wanted two disconnected asymptotic boundaries with entanglement, that's the standard way to get it. There's not those. But here you have a closed universe, which is some obvious.
Yes. Yeah, so just talking about that point, maybe use this.
And this entanglement, wherever it is, goes to zero as beta goes to infinity.
Yes, that's right. Yeah. So this entanglement here, everything is order 1. And if beta goes to infinity, that entanglement, at least, yeah, it's going to be.
It seems reasonable because the throat is, the neck is going so long, but
So much Euclidean evolution.
so much evolution.
I mean, one way to say it is effectively this large beta will project this state onto the vacuum.
Yeah.
Right? So on this side also, if the vacuum is a unique state, there's nothing to be entangled.
But I was just curious, can one actually compute, then you can compute
it using the path. You can compute it using the path.
some mark.
Yeah, that's RT. So that's one description. The other description, of course, is since we know this is a state which has low energy, so it has energy of order 1 and entropy of order 1. This is some.
Yes.
Yes.
And the closed universe, you can construct it independent of beta in some sense. Right?
Independent of, I mean, the only thing that beta was important for was to make it dominate.
Okay.
If it was small beta, then there's a different solution which would dominate, which is where you have a black hole and this thing goes through it.
No, yeah, I was thinking of the large beta. No matter how large beta is,
it
keep
always.
that closed universe part fixed and take beta.
Yeah.
Right.
I see how this point I didn't understand that if beta became very small, what did you say? You won't get
The black hole dominates. Like there's a different solution, right? You can have a solution where the black hole has a large amount of matter in the middle. You just have a connected geometry. It's like the thermofield double, but now put up with this with matter.
that dominates. So
That will dominate with this. Just because Hawking page.
But your puzzle is going to come in the opposite.
Yeah, it's in the it's important that
Beta
there
goes
is
to
this.
infinity. That's
So it's really in the sector, in the low energy sector. Very good. So now in this description,
like a Hawking page transition.
it's a Hawking page transition. It's just Hawking page.
Gets replaced by the interior.
Yeah, Hawking page with this perturbed object, like with this extra matter. Very good. So the description 2 is, of course, just using the extrapolate dictionary. We think we understand all of these states that are of energy order 1 and entropy order 1. You can just construct them using the basis of low energy operators that you have in your theory. So I'm just going to write that generally as psi I is a sum over j and k of c I j k. Some coefficients that we'll figure out. Phi j left, phi k right, acting on the values.
You're saying energy order 1 because you're in the Hawking page.
Exactly. So just from measuring the energy here, you'll find that it's order 1, like it's near the value. And so these phi j and phi l are basically phi j left and phi k right are just basically operators that would create like few particle states in these AdSs. Right? So what, depending on your operator content, there's going to be some set of low energy modes, and this is just the Fock space.
So you're accessing very high energies in the closed universe, roughly speaking.
Right.
Even though you're at very low energy.
Correct. So let me say that.
So then I didn't get.
Yeah. So let me just say that differently. So here, the state that is living here that we're computing on the CFT is a very low energy state. So these states are all things which have low energy and have a description in terms of just these particles floating around. But these coefficients are somehow capturing the fact that there's a very high energy thing that's happening in the closed universe. So the coefficients very sensitively depend on the fact that we had this heavy operator and it knows about the black hole spectrum, for example. So there's some high energy UV stuff that's secretly hidden in the coefficients of this wave function, but nevertheless, it's a state which is well within the low energy limit. So the state itself is a very low energy state.
So these OGs are just few gravitons.
These are just few gravitons.
And then, but then the CJ, how do they?
Let me say what CIJK is. CIJK, you can just compute using a path integral. We can just compute. It's basically this path integral. So we had this. We constructed this state with this operator insertion, right? So this is OI, right? And now we just want to take the overlap of that state with these low energy states. These low energy states can be just described as a sphere with some operator insertions. So you can think of this as phi j, phi k, and OI. It's roughly like an OP coefficient between light, heavy, with some Euclidean evolution. Okay, so these things are.
This guy was heavy, but it was made out of simple traces.
Yeah, but the net effect is that it's like in the black hole space. Yeah.
But a very special part of that.
Special part of that.
It's not so clear immediately. Are you going to say that this is some chaotic thing?
I would say, I mean, that's how you would interpret this result, that it's chaotic.
It's not so clear.
I think we don't have a clean understanding of it from the CFT directly. The only way we have some estimate of this is by filling in the bulk and looking for what it is. So I'm not sure if we know exactly how it acts.
I mean, sorry, just to understand. You're saying CIJK is a chaotic kind of thing.
I thought that's where he's heading.
Yeah.
But given that this is like some operator made out of gravitons, even though a lot of gravitons, it seems less clear to me that it's chaotic. Because it's like a collapsing dust shell, as you see visually.
Yeah.
And that's not the kind of thing that causes chaos. Once it's made a black hole, it's causes.
Once it's made, but here that's sort of what's happening, right? Like, I mean,
eventually it will become.
Eventually, yeah.
But the state itself is what you're putting. That O is creating the stuff going in. That stuff was not by itself chaotic, right? Meaning, for instance, let's say, suppose what we could have done is taken the source for the dilaton.
Yeah.
And turn it on at order n squared.
Yeah.
That would have been an example of such a state, right?
Yeah.
That is certainly not chaotic, right? It's just a shell of dilaton going.
Coherent state.
Yeah, yeah. Now dynamics will eventually make it.
Yes.
Will scramble and so on.
Yes.
But what you're putting there is just that shell of dilaton.
But that information then must be there in the OP coefficients to start with, right? Like, where did it come from? Like, what does it mean to say, like,
Okay, I see what you're saying.
Like, it's just unitary evolution after that, right? It's not introducing some new stuff. Because you have a large number of them, it's not so clear that it's not so chaotic.
You're saying you put a complete set of states
Yeah.
in the middle.
Yeah.
And it will access. But it could be very tuned so that, somehow the bulk picture doesn't feel chaotic, right?
In the beginning, I agree that there's a lot of structure.
I mean, like if you try to compute Botox just with the shell before it thermalizes,
Yeah. You'll be fine.
I'm surprised you get right? That sounds too much. No horizon, nothing, just some, if I understand right, some shell outside, you can completely talk, I suppose. But yeah, so that's a little.
Yeah, you need to wait for black hole formation.
Formation,
Like,
yeah.
But like, it depends on what you mean by chaos. If you mean things like spectral form.
Yeah, we mean more like random matrix
Random matrix
behavior of the
behavior.
matrix elements. That's what we're looking
Illusions
for.
will show similar behavior.
It's that sense of chaos that we want.
Because they will form wormholes the same way that.
They're in the same spectrum, right? They're still like in this dense spectrum.
Then let me just ask, so in that sense, I was thinking that J and K take only few values.
Very few.
So the random matrix behavior is in the sense that I has many
Yeah,
states.
it's roughly like I is labeling some microstate. You could change the microstate a little bit, and then change everything. Yeah. Another way to say it is one more way which will become relevant is, for example, at a given value of n, these things take on some value, but if you change n by 1, it changes drastically. That's the other. That sort of gives.
Wait, are you saying that in n equals for angles?
Yeah.
I take trace f square, coherence somehow, trace f square to the power n square, let's say.
Okay.
And then small. Are you saying that has some crazy behavior?
I think I am saying that.
It's crazy in the sense of like there are exponentially many such states, even though not comparable to the black hole entry. Much smaller than the black hole entry, but still exponentially.
Exponentially. So of course, if you're saying it's crazy in that, that sounds reasonable. But it shouldn't be crazy in n square, in e to the power.
Sure. But it doesn't, I don't think it matters whether it's
It's crazy in what sense?
exponential in some function.
The Fock space of gravitons grows large at n. That's what he's saying. And it's crazy in that. That sounds reasonable.
But it's still
It's still scaling with some power of n.
Some power of n, but not. But it's not black hole.
Okay.
Yeah.
It's a little hard to see from here if that's.
I mean, it's not entirely clear to me that it's certainly a big Hilbert space. Whether it becomes random.
Also, it takes that kind of. Yeah. I mean, suppose one were to form a state that would you can form states that for a long time would become a gas of gravitons.
Yes.
And then eventually collapse into black holes, but that would be some, very late time. If it was that kind of state, at least, it should have a hard time accessing the black hole. Because there's another kind of state which is really going boom into a black hole.
Yeah.
But somehow,
There should be some
Yeah, like a more concentrated shell versus just long
exactly.
and slosh back. Yeah.
Yeah, I mean, there should be some hope of seeing that these are different. That's true. It's also not clear to me that it's going to be. I'm not sure. Maybe it's important, but
it's not important. We can just go on.
Yeah, right now I'm not sure if it's important that it's going to be n square or n to some power. I always thought it was n squared, but maybe that won't be important. But we can think about
Just to form a black hole, of course, it has to. I would have thought some coherent state, classical collapse, right?
Yes, it's classical.
N squared, right?
No, energy is n squared, but like whether this erraticness is like controlled by n square or this smaller n to the 9/10 or whatever. That thing.
Yeah, what might be important is the time scales. If it collapses into a black hole, then at time of order 1, it starts behaving quite chaotic. Whereas here it might be a time of order n square.
So if we think about, if we just prepared this state, if there was a Euclidean boundary, for example, so if instead of cutting off this outside part, if I had a small amount of Euclidean evolution, I think that state would be a black hole at t equals 0, right?
Sorry, say that again, please.
So I'm just saying here, if I had this operator insertion and some small amount of Euclidean evolution, prepare some state, then this state, so forget about one side, just let's look at one, let's just think about this one side. Then I think, for short enough beta at least, or more generally, the state at t equals 0 would already be a black hole, right? In Euclidean, it looks like it starts from the boundary and goes in, etc. But the geometry at t equals 0 is already, that shell is already in the interiors. Like for example, this geometry, where this thing is already behind the horizon, on this slice, you don't see something like something falling from the boundary and becoming a black hole. It's actually already a black hole. So even though in Euclidean it looks like it's kind of systematic or something, it's already chaotic at t equals 0 here.
So you,
That should be there in those matrix elements.
the only thing I'm a bit confused there is, I could have understood why your O and M state, if it's heavy, is already inside it's already inside the black hole because you have a non-trivial beta and you're going to Lorentzian space.
No, it's because O is heavy.
It's because O is heavy, right? Okay, but here, this state, if I were, you're not going to try and connect this second psi I directly to a Lorentzian geometry.
No, I am.
You are. But here it wasn't clear to me why it would be a duck.
It's not. That's the confusion. So I'm getting to that.
One last comment on it, Sharad.
Yeah.
One way of creating a coherent state is differentiated with respect to coupling constant. That will bring trace. That's right. So if the claim is that operator derivative with respect to coupling in n equals for m, you can take the derivative with respect to coupling and put that coefficient large.
Okay.
Meaning we keep it n squared. That's what the Lagrangian naturally does. It naturally keeps it on n squared.
Okay.
If the claim is that is some crazy thing, that sounds suspicious.
Many people. It's not just one.
No, but I was thinking you just take the derivative in the normalization where you're getting it.
He's saying it's like taking the 3-point function,
Many
differentiating it with respect to the coupling constant.
Yeah, I mean, I'm preparing a one particular shape.
Yeah.
But it's all dilettante.
All dilettante.
All of them, all my modes, n square modes in the same state. Because I want to do the maximally coherent thing.
Yeah.
Okay, that is basically taking derivative with respect to coupling.
Yeah.
This sounds like a very smooth object. I just feel okay. We can go on. I don't want to delay it. We can talk about it.
Derivatives,
Coupling, yeah.
which is the natural
Yeah.
But yeah, so here, like, I mean, I guess we could just literally try to phrase this question in terms of n equals 4, right? So this is your derivative with respect to the coupling. That's this yellow thing, and then we're just taking that overlap with some
some
light operator.
Some partition function with derivative with respect to coupling and
Correct.
particular point and two things.
Yeah.
That feels very smooth to me. I might be wrong, but it doesn't feel like crazy.
Understand why? So to create the shell, you have to insert a lot of these single place
Yeah, that's the thing. From n square
What
there.
the
Yeah.
n square number of derivatives, just like source.
I think that's maybe where the chaos would be.
I was thinking you just take the derivative and put large coefficient.
Want to put the large.
Meaning, say, suppose you take your Lagrangian to be n squared by lambda. And I take the derivative in the with respect to lambda.
Yes.
That's already taking this kind of thing we do in gravity.
Yeah.
So that puts a lot of stuff. But we need to get to the end of it.
There's another thing which we have to be careful about, which is that this thing, I mean, needs to have this approximate global symmetry or something like that to have this description. One thing that may happen is for that particular operator, you never get this solution. You just get the solution which connects separately in the Bryant ket, and then this may not work. So you need some kind of operator which does that, and it's not perfectly clear that this operator.
Pratik, just to understand this, are you saying that at t equal to 0, you can have this black hole phase as well?
Yes,
If you insert heavy enough operator.
if beta is small enough, and I mean, there's some competition between the heaviness of that operator and beta. So if I make the operator very heavy and then have small amount of time evolution, then I'll end up with a black hole. If I really cool it down by having a large amount of beta, then I have this.
So in fact, you're sort of saying there is a third possibility.
Yeah.
Which is, I mean, that's one, that's second, and the third is just that you just don't get the closed units.
Well, that would be a different description one. That would just be, this is, the difference between these two descriptions is this is prepared using the gravitational path integral, and this is done using the extrapolation. If that was the case, then description one would just be different. It would not be this solution, it would be that solution where they just connect separately in Bryant ket. So here we're positing that we can find situations where this is the dominant solution.
That's all.
Then this is description one, and then this is.
So it could have been that other thing,
Absolutely.
but you can make sure.
We just need situations where that thing dominates, like the connected thing dominates. And we know we can construct, like Marolf and Santos construct those kind of
These guys don't.
Yeah. The connected thing includes.
the CIJ, the
Yeah.
path integral that you do over
Yeah.
there, that doesn't have a clean bulk description.
No, not obviously at least. I mean, I don't know. So yeah, that's an interesting question. If this is erratic, then of course we expect that it shouldn't have a good gravitational description. If it was that you could have had contractions within the shell, then you would have had a smooth description because then you could have the shell just contracting within itself or something like that. And then this is some smooth geometry where that's happening, and then this would be disconnected. So it's very closely tied to the fact that there is a connected one, so that there's no nice gravitational description for these coefficients. There would be a similar a construction for squares of these coefficients, which will have some nice.
Yeah, so this in between region is, what is the connection with the Marolf samples?
I'm just saying there, if you have some solution which is connected like this, then just draw tubes like this, long enough tubes, and this will give you a dominant solution to that.
This guy, which you see was
I mean, for now, all I'm doing is changing the boundary condition slightly. Like instead of these closed circles, I'm adding these extra tubes and then looking for the dominant solution to that. And I'm saying here, just fill in thermal AdS in these things. That's the dominant solution to this new problem.
So this is a small modification of the Marolf problem.
That's all I'm saying.
okay, but just to make sure, in that case, you have sort of your at least whenever you cut, you have 3 disconnected components, right?
Yes.
And here you would have 2,
No, 3. 1, 2, 3. It's exactly the same.
Sorry, did you say that if the OI would contract within itself,
Yeah.
then here this guy would just gap on?
Yeah, so the picture there would then be that this shell, instead of going this way, it would go that way, it's in that way. And then there's nothing on the tensor. So it is closely connected to the kind of operator devices. Okay, very good. So that's really what the puzzle is. So the puzzle is we have these 2 descriptions for the same CFT state, which have different descriptions. One has a closed universe and the other one doesn't. So this one, as a Lorentzian geometry,
the same state. I'm missing something. There's some overlap.
no, it's the same state. It's literally the same psi. I'm just taking this psi and writing it in that basis. That's it.
But I would say that
This one has the heavy operator and the other.
But you projected it down to small energy, so it just has energy of order 1. So the only Hilbert space is really accessing is the part which is like built out of this box space.
there's a similar puzzle in the black hole case, right? Like there's on the one side there's the thermofield,
It's exactly the same as
state which
that.
you can write at the energy eigenstate basis.
Yeah.
as a-
So what I was saying is the
There is a very small overlap. There'd be a very small overlap.
between what?
Because this guy is a heavy, what I'm saying is if you take the O and you hit it on these E's,
Yes.
maybe it naturally excites.
So what it does is this O excites the energies a lot, but then we have a large amount of Euclidean evolution which cools it down.
Cools it
So the
down.
state is dominated by energies of order 1. The support on the higher energies is completely killed off.
It's gone, but I'm just saying the coefficient in front of that support would be very small, right? Because
No, it's not. I mean, the bulk tells you that it's not. The energy is order 1.
the energy of projected down to order 1.
Yeah.
But I'm just saying the initial very highly excited state had some tail
Yeah.
down to energy of order 1. That tail is some, let's say if you had a normalized state to begin with, is some very small tail.
That's right.
Okay.
That's
So
right.
you
So maybe one way of saying it is initially you had something which had a large energy peak and then a small energy tail at low energies. And we can just think about the Euclidean evolution as a projector onto this small energy sector. So you're really picking out that tail. Now all that's left is that tail.
I agree. But okay, you can pick it out through the projector Euclidean evolution.
Yes.
So what happened to the beta that we're doing? They are now inside CID.
Yeah, so CIJK is this path integral. This path integral includes beta left and beta. Very good. Okay, so now, and the bulk description of this state is just 2 AdSs. This is AdS left, AdS right, in some complicated state which is entangled with each other. Right? So here, note one important thing is note that the state in these AdSs was mixed. Right? So if I looked at just the AdS left and AdS right, that's mixed because it's entangled with the closed universe. There, it's a pure state. Okay, so this is very much in the flavor of the black hole information paradox. There's a construction that we have. So this is roughly like the CFT answer. This is like the unitary picture where we expect that this is the answer that we get. It's a pure state, so it's like the Hawking radiation coming out pure. But in this, we don't have a description of the interior, which here is the closed universe. The closed universe is completely lost in this description, and we have a complicated state fixed by these coefficients. These coefficients you can morally think of as the S matrix. That's like the black hole S matrix. So that's the analogy with the black hole information paradox. In this description, we have the right state, we lose the interior. In this description, we have the wrong state. It's more like the Hawking state where it's mixed outside, but we do have the interior. Okay? So it's exactly the same kind of puzzle that we talked about in the context of the black hole information paradox. So it's a much simpler setting where we see the same issues and we can try to understand what happens here. So we can talk about all these different.
And one state is in the CFT Hilbert space.
Both are in the CFT Hilbert space. It's just what the bulk description is.
So the pure state I understood in the CFT Hilbert space.
So there's a pure, so psi I is a pure state in the CFT Hilbert space, period. Now, there's two bulk descriptions for that same CFT Hilbert CFT state.
Yes.
One is analogous to having just the radiation, which is just the two AdSs in some complicated state. Pure state, still complicated pure state. The other description is having those things, but being entangled with a closed universe with some mixed state on the exteriors. Now you can ask the same sort of questions. So the analog of the page curve here is why is the entropy in this state 0? Right? So we can ask in this description, the CFT entropy needs to be 0. And the reason it's 0 is because you can, if I compute the entropy of these two universes, you include the closed universe as an island. It's advantageous for you to include the closed universe. It reduces your entropy while costing you no area. So again, the answer of the entropy is completely consistent between these two descriptions. It's exactly analogous to how we find the page curve. Nevertheless, you see that in one case, you have the correct state. Correlation functions that are computed here in the asymptotic AdS region will be perfectly accurate and give you exactly what you find from the CFT because these coefficients were sort of by construction chosen to give you the correct answer in the CFT. It's just the extrapolate dictionary.
Sorry, what is the analog of RT curve for RT?
The RT formula is, so here we're trying to compute the entropy of these two boundaries, right? So there's one AdS boundary here and one AdS boundary here. Naively, those regions have a mixed QFT state, right? So the region here and here is mixed because it's entangled with the closed universe. Now we apply RT to these two boundary regions. What do you find? You find that there's an island. The island is this region. It's the closed universe. Why is it an island? Well, when we're doing RT, we minimize over the generalized entropy. And it's advantageous to include the closed universe as an island because it drops your entropy. It removes all this entanglement that you have with the island, but it doesn't cost you any area. The closed universe doesn't have a boundary, so there's no area. So the RT formula...
That slice on the closed universe will not have any area.
There's no area. It's a closed circle. It's a sphere. There's no boundary to it. So you include the entire closed universe.
And to put it another way, naively speaking, the closed universe has many states.
Yeah.
Because it's generating a huge amount of entanglement.
Yeah.
But there's another picture in which there is
Exactly. So now, yeah.
So
Yeah.
the entanglement is basically reduced by given this universe is order 1.
Everything is order 1.
So how do you even decide?
I think your question is it like a well-defined entanglement wedge or something? Like,
Yeah, I mean,
it's an order 1 difference. Yeah. Very good. So you can do the exact entropy calculation, even if you don't believe the RT formula. Firstly, the RT formula will be corrected by errors which are controlled by the amount of entanglement you have. So the difference between the leading saddle and the subleading saddle will be e to the minus SCL, where SCL is the amount of entanglement between the closed universe and the open universes. So like in the black hole case, errors are controlled by e to the minus A over 4G. The role of A is played by the amount of entanglement with the universe. If that's like 1,000, then the RT formula holds to great approximation. Even if you don't have that, you can just do the exact path integral and you still nevertheless find the dominant contribution from this thing. So it's either way going to be pure.
Are you engineering this closed universe in a way that SCR is something?
I don't need to. I'm just giving you an example where you could just directly trust the RT formula. Like if beta is not too large, then there will be a significant amount of entanglement between the AdS and the closed universe. You can of course tune beta to be really, really large so that there's almost zero entanglement. So that's a situation that holds. But I'm just giving you a setting where the RT formula is trusted.
And just to understand, in the field theory,
Yes.
You have two different predictions for the state. One prediction is that which comes from bulk field, the bulk effective theory, and seems to suggest that the state is mixed. Whereas the second prediction, just by using CFT logic, tells you have your pure state. And that is, and you have to resolve that contradiction, very much like Hawking.
Is very much like Hawking, very much like.
Yeah, but is that accurate?
That is accurate. And I just wanted to make one distinction there, which is the state looks mixed just like in Hawking, but of course we use RT, then you find purity. But it's exactly the same thing. Yeah.
But I thought both these descriptions
Yeah.
are pure states in,
They are pure
in the
states.
tensor product of the two
That's right.
theories.
That's right.
It's just that their bulk description in one case seems to suggest you have entanglement.
But you can ask the same questions. Like this is like the Hawking state, and you can ask in the CFT, this is a pure state, and if you ask me to test that, I would just compute the entropy and say, oh, there's an island. The entropy is 0. There's no contradiction between these two descriptions. But then you can ask more fine-grained questions like, can I measure the correlation functions of things in the exterior and so on? And this description by construction gives you the right answers. That description doesn't. That description is more like a mixed state in the, it's like not knowing the S matrix in detail. So of course you won't compute the S matrix elements in detail correctly. So it can't give you that. Nevertheless, it gives you the right entropy.
I mean, if you just take the semi-classical Hilbert space
Yeah.
that you see,
Yeah.
and in that semi-classical Hilbert space construct the boundary
Yeah.
state, it will
Yeah.
look mixed, right?
Absolutely.
No, absolutely it will. But I thought the moral out of the island calculations
Yeah.
are that if you do it very carefully,
Yeah.
not only for entanglement entropy, but
Very
for
good. So
then you would get.
that's what has been said. I don't think there's any clear calculation of that. And if that is true, then you should be able to do it here. So the point of this model is every question that we could ask there, we can ask here. No, I'm just saying, even in this model, we don't know an answer to that question. So there's no concrete calculation in this type of picture, like directly from the gravitational path integral, which will reproduce accurately correlation functions of things in the exterior, which care sensitively about these coefficients. And the reason, as Onkar was saying, was these coefficients, computing them directly from gravity seems hard if they're erratic. There's no mechanism we have in the bulk to compute those coefficients. Just like the S matrix, just like the black hole S matrix.
So the RT formula is the one thing.
Is the one thing that
we can, but nothing else.
Yeah.
I mean, this really depends on this thing being more erratic than you can see in the bulk,
Yeah, it's in
which is not totally clear to me.
Sure.
Because if you could see all the erraticness by hand, you can compute it.
in the bulk.
In the bulk. So its question is the erraticness more or less than the Fock space of gravitons? Right?
Yeah.
That's not totally clear.
I mean, so there are simpler models of this, like in 2D gravity, where people even use, say, the SYK model and construct these operators. And there, because you can do numerics on SYK, you can actually test that there exist such operators. So there it's clear. In N equals 4, I'm not sure.
Just say, I was also beginning to wonder. So in JT, what is the statement?
Yeah, so in JT, it's a bit more complicated. In JT, it's a little more complicated.
Or you can tell me later.
Let's leave that to later. We can talk about that later.
Sure.
Let me just, so since we've said all of this, so you've seen what this puzzle is, let me just recap everything as Shiraz was also asking. All the different options that we laid out on the table, this flow chart sort of thing. So all you need to remember is these two descriptions and the puzzle between them. Let me just say that very quickly, then we can end. So the major options that we considered earlier were, of course, we spent a lot of time talking about complementarity. Right? So the first option we talked about was complementarity. And in this setting, it's very easy to understand what complementarity should mean. It should somehow mean trying to make both descriptions compatible. Right? That's what it really means. While, and remember that there were two versions of complementarity that we really talked about. There was the initial idea of, three versions. But right now I'm talking about the star version, which was this idea of non-isometric codes. It's the idea where we take QFT on curved spacetime as it is, don't talk about observers or anything like that. And then we just say there's a map from the effective field theory Hilbert space to the fundamental Hilbert space. And we take seriously the inner product on the fundamental Hilbert space. This would imply, in those situations, what was said was there's very small corrections when you try to compute overlaps here between simple states. So if you put a complexity bound, there's not much of a difference between the inner product computed here and here. The errors were controlled by e to the minus a over 4g. The analog of e to the minus a over 4g in this setting is the entanglement with the closed universe. So this gets replaced by e to the minus s closed, which is an order 1 number and can be made parametrically small. So we can have a gigantic universe. As we said, the mass can be huge. This universe can be gigantic. But the entanglement between the closed universe and the exterior is a separate parameter that we can play with. We can set that to be basically 0. And through beta. You can just project onto the ground state. Which means that this is really no help. So the non-isometric code is basically doomed to failure. In which case you can take two options. Either you can say that the non-isometric code is the wrong idea for the black hole as well. In which case, I mean, instead of taking the fundamental inner product seriously, we should perhaps take the EFT inner product seriously, which would be basically undoing all of that non-isometric codes idea in the context of black holes. Or you can say that the closed universe just doesn't exist. You can say that we take this non-isometric code seriously so that we predict that the closed universe doesn't actually exist. And this is, I mean, some people actually told me that this is what they believe. And this is a gigantic universe which is well in the regime of effective field theory. And nevertheless, they suspect that it may break down for some non-understood reason.
I'm not able to understand this short during comment. Sorry. So the H effective mapping to H fundamental was the non-isometric code. Is that right?
So this is just a general fact that from the effective field theory, you have this map to the fundamental code, which is because you're projecting down from a larger Hilbert space in the EFT to a smaller one, which is bounded by e to the over 4g. Right? So that was what we had in the black hole setting. And then there was a question of what's the relevant inner product for the interior observer? You can either say it's HEFT or H fundamental. What was said there is H fundamental, and we were trying to embed everything in the CFT. And the claim was, since there's only small corrections, it doesn't really matter, and an infalling observer just sees EFT physics as long as they only do simple operations.
Simple operators.
But simple operators.
Yeah.
Okay. But here you can say all the same words and it's still doomed.
Okay, but I'm so sorry, at the risk of slowing everyone down, to say the same words in your context, we take description 1.
We take description 1.
And we take some simple operators
in the closed universe.
In the closed universe.
Like we want to describe infalling observer. Infalling observer here is observer in the closed universe.
Right.
And we can ask what's the relevant physics for that observer. For example, what are the matrix elements they would compute between two different states in that in the closed universe and so on. And that is drastically different from the thing you would compute on the CFT. Because on the CFT, you just don't have enough states. Like you basically killed off all the entanglement and you're in the vacuum. How does that even know about what's happening in the closed universe? So there's no way to recover EFT physics in the closed universe if you take seriously that the fundamental inner product defines physics for that infalling observer.
Meaning the closed universe could just be doing what it does. You can't change it.
You can't change it, and you can't even read it off. Like there's nothing like there's no information about it.
Yeah, but I mean, the most stark thing is that it looks like there's a huge Hilbert space. But you're accessing only a small part.
Yeah.
So if it's like destiny, you just are going to follow this.
Right.
Then perhaps that you are constructing one state inside what looked like a big Hilbert space.
Right. But then the problem is we don't know how to embed that into the CFT. So then it would
but then you could embed it. If it was just one state, there's no problem embedding.
No, but then good. If you have one state, then you can embed it. But of course, we think that there are non-trivial states in the
So then the question would be, you would have to formulate some thing that you want to do and say that cannot be embedded in the CFT. You want to change something,
right?
And then you have to say how you try to change something given consistent.
There are non-trivial operators in the closed universe, and you can ask how, give me an example of such an. Like for example, I mean, if in this shell case, it's simple to understand the shell case. Like one thing you can do is just
press it to the shell.
Yeah, press it to the shell. Like take some particle from there, put it somewhere else, something like that. That sort of stuff. There's many non-trivial things we can do to the state of the closed universe, which are perturbative, and those should be described by EFT physics. I mean, that's what we would expect.
At least we expect there's no radical breakdown of effective field theory. You will certainly have relational observables.
Yeah.
in a big closed universe, right? Many things going on, that's where, and so on.
Yeah.
And naively, that's the effective field theory expectation of some big Hilbert space.
Yeah.
But just to play devil's advocate,
Yeah.
suppose you say that all this is a trick for computing something on the boundary. Right?
The bulk, right?
The bulk.
Yeah, absolutely. That's one way of.
I'm going to give you a prescription for how to compute something on the boundary.
Yes, yes.
And this prescription is well posed.
Very good.
And there's no internal contradiction from that point of view, right?
And then I would say then you would have to say the same thing about the black hole interior. I mean, because it's essentially the same thing, you would have to there say, as I was saying yesterday, the page curve is giving you the smooth interior, but that's really fiction. Like that's some calculational trick to compute the entropy of this.
Something beyond the field theory, right? To make this.
No, should I to say, what is the tool to compute something on the AdS CFT? But what about the AdS? Sorry, I didn't answer your comment.
Yeah, I say that all we're interested in is computing field theory observables for a moment. Okay. Now, in doing that field theory observable, it's hard to make sense, as far as I can see, of trying to change what the closed universe will do. You've set the closed universe in some state, it will evolve.
Okay. But you can consider different correlation functions in the field theory and they would change the state of the closed universe.
Okay, but whatever you do, you get an answer.
You get some answer.
And it will be consistent from the field theory point of view.
Even that is not true because this thing, like for example, if it's an erratic thing in the field theory, we don't see how to reproduce it from gravity. So you're not going to get that answer from the closed universe. Like as a simple example, like if I took two different operators, then we can try to compute the overlap between psi I and psi j. And psi I, psi j will just be delta ij, just like we saw previously, and then mod psi I, psi j squared would be equal to e to the minus s, independent of I and j. Where S naught is S, C, and S, the entanglement with the
Sorry, I think just this psi was the operator you wrote.
So I can just draw a picture for this. So this is like what we drew before. Is this thing. So we had this torus type thing with some operator insertion here. That's I. And now I'm going to draw this. That's J. And then I'm gluing these together to compute the overlap. What I'm saying is if I and J don't match, there's no closed universe contribution here. So this is just 0. But on the other hand, I can draw another such thing and then have these insertions with this being I and this being J. Then there is a universe because I'll have a universe here, I'll have a universe here, here, and here. And now this one swaps here and this one swaps here. So it's a replica wormhole between them, which will contribute to psi j squared. So this itself, in some sense, is a contradiction already.
So yes,
even at the field theory level.
The field theory observables will be incorrectly computed.
Yeah, it's computing it in some coarse-grained sense, if that's what it's computing.
Nice.
Right. This EFT observer also see this erratic brain sitting around, right? Erratic.
Yeah, so the whole question is like, we can kind of make sense of this. So from the field theory perspective, maybe you just say, okay, this is computing things to some approximation by doing some coarse grading average or something like that. The hard part is to now translate that to saying what does this mean for the bulk observer?
Yeah.
That's what I'm interested in. And so here what we were trying to say was if you take seriously that things you're computing on the CFT is relevant for that bulk observer in some sense, like transition, amplitudes, etc., then this, I mean, what you'd have to say is if you have a single CFT, this answer just is inconsistent. There are going to be other effects which will change this answer so that you get that erratic answer. But then obviously you have to suspect that the bulk description of that closed universe is also suspect because this answer was wrong and it has large corrections. So it would call into question the description of that bulk observer as well. That's really the
put it in another way, which is what you already said. If you believe there are well-posed observables in the big closed universe,
yeah,
it seems hard to extract them.
Yeah.
There doesn't seem to be a boundary.
Which very, very nicely brings me to option 2, which is AdS not equal to CFT. So the other way we could imagine things working is in some way in which the CFT is not the complete description of bulk physics. One such picture is the second set of things that I talked about, which was the Marolf-Maxfield type picture, which is where we had this label alpha. So one way to understand what was happening here was that the first description was in the Hartle-Hawking state. So the first description, we just added this boundary without any extra boundaries floating around. We just added we created this state in the no boundary state. This would be an average over alphas, right? Some state which has some distribution over alphas, and we're averaging over them. On the other hand, the second description is in a fixed alpha. Because what we did was use the extrapolate dictionary. The extrapolate dictionary is something about a particular CFT. We cared about the particular coefficients that showed up. Those OP coefficients were OP coefficients of a particular theory. So then this a priori in this picture, where you do have non-trivial alpha states, are just different states. There's no contradiction at all. But in order to say that, you need to say that there is a non-trivial set of alpha that we're averaging over. The gravitational path integral has these non-trivial labels which capture the physics. And then, of course, alpha captures whatever's happening in the closed universe. So you can have non-trivial operators which change alpha, which will change the state of the closed universe. So there's really no contradiction here. The only issue is it's not AdS CFT. It's not, the CFT doesn't know anything about what's happening in the closed universe, and there's some other degree of freedom which is capturing that. It again would boil down to something similar to what we said in the page curve case, where you get the Hawking curve if you really trace over alpha. You don't have information of alpha. But if you measure alpha very carefully, if you're basically in a fixed CFT, then you have this other description where you've lost the interior and you just have this out state. So that's there's a similar thing which is related. So of course, this AdS not equal to CFT could mean anything. There could be any degrees of freedom which are describing this interior. It's just that it's not captured by the CFT in particular. And there's a whole host of things that have been tried in this kind of idea, including this averaging over n and some coarse graining over the microstate, etc. They're all in this class.
And just to be sure, the closed universe can exist for arbitrarily long time.
The time that it lasts for is controlled by the size of the universe, and that can be made arbitrarily large by taking the mass to be really large. So yeah. So that, okay, maybe that's why I had that formula.
Actually, at least in normal Robertson Walker can be.
Yeah.
In the mass of that closed universe related to how the T
Yeah.
If I were a real AdS CFT purist, would I say maybe your interior geometries were unstable in the same sense?
Yeah, I mean, so one way to poke a hole in all of this is to say Marolf-Maxfield, Marolf-Santos. Yeah. So one way to poke a hole in this would be to say that no such geometry ever exists. If you've done that, I think you've basically solved the factorization problem. Like if you would have then figured out how to see that the gravitational path integral just factorizes, because then you've showed me how all of these things just don't matter. That would also be amazing. That would be a nice way to get around it. It would necessarily, I think it would undo a lot of the progress we made in trying to understand wormholes, etc. But that would be also interesting. That's one way out of this. So this stuff is based on being able to construct description 1 in the way I said. People have tried to poke holes in that, and that's also a valid thing to try. But then, of course, whenever we do something here, we should always think about what that would mean for the black hole interior. So then there's some instability, etc. I mean, whatever you say about this closed universe morally applies to the interior as well. So it's going to mean something. Okay, very good. So I'll just say a few more things just to lay out all the options. Of course, one option is just a firewall. So firewall here has some more concrete meaning. I think the firewall would roughly be what you just said, because you would then say, I don't have all of these labels alpha to capture this smooth description of the interior. All I have is this description 2. Description 2 is manifest, like extrapolate dictionary is sacrosanct to AdS CFT. We want to keep that. Once you say that, and you say there's no two descriptions of the bulk, then you're basically left with this description 2, which doesn't have a closed universe. Closed universe is like interior, not having an interior is like firewall. So in that sense, this is the firewall scenario. And perhaps, I mean, if this is really what's happening, maybe in this example, we can make it sharp by trying to understand what instability it has, etc. And the last thing, which seems to be the trendy thing,
Nonetheless,
Yeah.
nonetheless, it would give you some. Ignoring that firewall would give you some good cost
it will
credit.
give you a good cost trend description. So it will say that the interior is a useful calculational tool. That's what it is.
But doesn't really exist.
That doesn't really exist. Okay. And finally, there's this one trend which is roughly like going back to complementarity. So remember that we had this initial version of complementarity, which was about trying to describe the physics of observers. So we were talking about physics of infalling observer versus outgoing observer, etc. In this complementarity double star picture, I mean, in complementarity as well, there's always an attempt to try to make them compatible and embedded in the same CFT. But if you don't do that, so if you somehow invent new rules, so if you say that somehow the rules of physics depend on the observer, and you have different rules for different observers, then maybe you can get around this, and this is what people are trying to do. It's not something I'm perfectly convinced about, but I'll just tell you what has been tried. So one thing that has been tried, for example, is in this closed universe setup, if you imagine that along with this shell, I insert an observer. So think about an observer as a world line here. So I just add some excitation, which is a heavy-ish but not very heavy excitation, just follows a trajectory from Euclidean past to Euclidean future. That person is the observer and is also going through this closed universe. Now, the new rule that's invented is to say that the observer is like a new boundary. So in AdS CFT, when we have boundaries, we obviously don't allow the first boundary to get swapped with the other boundary. We allow bulk regions to get swapped, but we think of boundaries as labeled. Now, if you think about the bulk observer as another boundary, then the boundary can also not get swapped. And so it completely kills off this contribution, which is a replica wormhole.
So it connects like that.
It always connects this way.
Yeah.
And so these arguments that lead to a one-dimensional Hilbert space rely on the existence of these replica wormholes. And if you kill off those replica wormholes, you'll find a non-trivial dimension for that Hilbert space. So it doesn't have a one-dimensional space. Now, how seriously to take these observer rules is not so clear to me. I feel like maybe they have some interesting thing there, but I don't think it has been sharpened perfectly.
So this is the kind of thing people try in De Sitter space.
In De Sitter space as well, yeah. I mean,
There you were allowing all kinds of.
In De Sitter space, like, I mean, so in the paper by Chandrasekhar and Longo, Pennington and Witten, they added this observer to try to make sense of this physics. But there it was still perturbative. Like they were still working in this Lajan expansion without including these wormhole effects. And there it was useful for them. Like it gave them a non-trivial Hilbert space for which they could compute an entropy. Here we're working at a non-perturbative level where we're allowing wormholes between these different spaces and so on. And in that case, the claim from these ideas is that De Sitter also has a one-dimensional Hilbert space. And that's something that they didn't see because they were always ignoring all these non-perturbative effects. Here, what's being said in these observer rules is now really add an observer and include these wormholes with the fact that the observer is treated as a boundary and you never allow the observer to get swapped. With those rules, you find a non-trivial Hilbert space, a not one-dimensional Hilbert space. So it helps a little bit, but it's not so clear that this is, I think it should be made sharper. This is what has been called observer complementarity. It's some attempt to formulate rules like the old complementarity, where you have different rules for different observers. As long as they're consistent with each other, you're good. That's all.
And then you have to say what an observer is. Right?
Yeah. Then you have to, then it opens a whole can of worms about what an observer is. Here, it's treated like a world line, which is like, infinitely.
It's a photon and observer.
Yeah, exactly. Then you have to ask, and then these answers may depend on what the observer is. Like, yeah. So it's a complicated question. So somehow we have to. I would like it to be phrased in a language where we say somehow some degrees of freedom or something like that. But certainly, this world line approximation is not going to be the final story. If this is the story. So that's what people are trying. Yeah. Okay. Let me start.
Yeah, let's do it. Because at the very least, you have a very nice sort of ternate setup where all the problems of black hole evaporation.
Yeah. That's how I mean, My sociological comment about this is that when we wrote this paper, we didn't even want to call it a paper. Like we wrote it as an essay for this Gravity Research Foundation thing. Because I mean, now that you know whatever I've said in the previous lectures, it almost felt like very direct to be like a direct consequence of that. And so I wasn't even sure this is worth a paper. And turned out it was worth a paper. But the way I wanted to think about it was here's a nice model where we can say everything that we said before, and it's easier to visualize, at least for me.
Well, it was important for you that this was the order one part of the data space.
I wanted to make that sharp just because otherwise you could get away by saying complementarity double star. Because there you say that there's a large amount of entanglement, so that controls this error between fundamental and EFT inner product, so we're good.
But even in complementary double star, once you went near, as you explained,
so there you could get away by saying that slice is not a nice slice because there's this corner where there's a singularity. Here you can't get out by saying that. That's what I like about this. I mean, to some people it was obvious at that level. Like Raphael, for example, said, why can't we just say that, like that thing? And but many people will complain about that.
Now, what was that point? You wait long enough.
If you just look at the slice which goes through very close to the end point of evaporation, area is really small. It can be made order one, like few times the plant size or whatever. And then it's the same thing. There's the non-isometric course paper would say there's large corrections. But there maybe you can get away by saying that slice includes some singularity, right? Because it's very close to this Planckian curvature. And so you may worry about that. Here, that's not the case. You have a completely smooth, gigantic slice with low curvature, and still you have all the same issues. In fact, like the history of this is that I first constructed these closed universe type solutions by looking at what's called the canonical purification in these island type situations. But there you end up with a large entanglement, and so it didn't quite help. And then KS squared essentially had this construction, but they didn't realize what they had just done. So Stefano and I basically got together to say this.
So I'm just trying to, in my mind, I'll ask you at lunch, but basically I'm trying to understand where we are.
Yeah,
I mean, in your view.
Yeah.
It seems to me that you're saying that the island stuff is interesting progress, but at some fundamental level just doesn't address the important questions. Is that
It answers a lot of questions.
It answers questions about how to compute the entropy.
Correct.
But let's say that we're interested in resolving the paradox.
I would say it's still an open thing. I was telling Harshit at breakfast today that before islands, people used to often say the definition of the black hole information paradox, like what it means to solve the black hole information paradox is compute the page curve. When you've done that, like people basically thought, of course, if you've computed the page curve, you must have figured out the mechanism by which information gets out, blah, blah, blah. I think maybe Andy Strominger said this. So
Strominger used to say about it.
Oh, yeah. And we have the page curve. So we've computed the page curve, but we haven't solved the problem.
The useful thing about what Andy said is that if you focus the question onto something one can compute.
Yeah.
You know, where it involves a number or a function or something like that. Could you suggest page curve prime? Something else.
The black hole S matrix, of course, would be it's really hard, yeah.
No, and should it? Maybe we can. Maybe your alpha vacuum the statement that non-perturbative theory of gravity, you'll have enough null states to actually go down to the gluons.
Yeah.
Maybe that's the eventual goal. But it's like asking you to compute, high temperature observables in QCD from the chiral Lagrange, right? Just sounds like an absurd thing to try.
Yeah. So this is why, okay, here's my take. I don't know, I mean, people may disagree on this, but I feel like what we're seeing is that holography is not helping us much. We've got to a point where we don't know how to use AdS CFT to, we used AdS CFT to see that there are tensions, but what's the right answer? Like, how do we figure what's the right answer? And so I think that is why maybe me and some other people have that's why this interest in JT gravity and like simpler models where we can work with the bulk is increasing, just because there we can just directly phrase things in the bulk and ask questions there, because holography doesn't seem to be helping us particularly much. But there, of course, there's the issue that in these simpler models, the answer is, of course, Marolf-Maxfield. Like we could always say there's non-trivial alpha states and that resolves the issue, etc. Even there, we don't have a nice description of these fixed alpha states and so on. So, but I feel like we need to make progress using the bulk.
Okay, but just coming back to that.
Yeah.
Just to understand, have a benchmark for what would be progress.
Yeah.
Asking for the black hole S matrix is just some crazy too much, right? Something that is potentially doable.
Yeah.
Like the page curve turned out to be.
Yeah.
But has more interesting information.
Can I ask a version of that? I mean,
If we are not relying on holography, say if we are not trying to translate things to the boundary, then you could imagine just formulating the question of correlation functions as measured by the infalling observer directly in the bulk.
As measured, you'd have to make precise. Right?
That's right. So this would require making that bulk theory precise enough to ask that question.
The nice thing about the this entanglement stuff was it was sort of clear what it meant.
Correct.
Clear what it meant to compute it in some way.
Correct.
Maybe not exactly, but here it sounds a bit vague to say as measured by the bulk.
Yeah. Yeah.
no, but I mean, can we not ask to make it very precise, but at least in the bulk, a precise question is if something happens in the island.
Yeah.
What would you have to do in the boundary theory to detect it? Right? That's a root question here, right? The island seems very useful as a computational tool for page curve.
Yeah.
But we don't really know in any kind of detail. We don't want to know the S matrix. That's too much detail. But is there, a coarse grained version of that? Bomb goes off in some suitably phrased way in the island. What do you do?
Yeah.
Right? I mean, that's the thing you're saying, right?
Yeah.
That there's a kind of tension in that whatever code people suggested. But then it's got the page curve suggests that the island is correctly being, recapped.
I mean, just as much as the
information is there in the Hawking ring.
just as much as the closed universe suggests that the data of these OP coefficients is in the closed universe. Like it's at that level. It may not be, it may be fiction, like as we said.
Well, wouldn't you say that at least the replica trick calculation suggests that the island, all the information content of the island is present in the.
That's also what you would say in the closed universe, right? In the closed universe, you could do a replica trick and convince yourself that what you did was an operator acting deep in the closed universe. But of course, we know what the operators are in this low energy sector. They're just things that change the state of the constants. So in some sense, in many of these PETS map calculations, this is okay, going back to your in the first talk, I think you were asking a lot about the PETS map. And I think that this is the issue. The issue is many of those PETS map calculations you could also do here. And you can put in the answer that here's this operator that does something in the interior. But here we have a clear description of what those operators should do. They just act on the exterior and do some change of state of this constants. So it's at that level that you sort of put in the answer.
So the PETS map in this context would involve these erratic coefficients, right?
It would, yes. Just like in the black hole, it cares about the microstate.
So it would be like some very crazy operator.
It would be some crazy operator, but nevertheless, it's a simple operator in the sense of complexity. There's a finite dimensional Hilbert space you have with these numbers, you may not know them precisely,
right?
But there's only e to the s amount of.
Sure. But you could have the effect that you desire, right? You could do some unitary on the asymptotic gradients and effect the close.
It is not perfectly clear to me what that means. Like you could have always said, so it's the same thing that I could say in the PETS map in the black hole, but here it's just starker, which is I just did some operation on this path.
Yes.
It's just some operation. I mean, this is a finite dimensional Hilbert space.
Yes.
It cares about details, but whatever. Those are just some numbers. Just using those numbers and putting in some unitary.
That's right.
Why interpret that as something that's acting in the interior as opposed to just something that changed the state of this radiation? That's the analog of saying here that operation has a very valid interpretation as just changing the state of the Fock space in the exterior and not doing anything in the interior.
Sure.
One concrete way in which I know how to make sense of that statement is if there's actually an ensemble and you say something like in each instance you're doing something that depends on the microstate of that ensemble. Like in different members of the ensemble, you have different set of energies and so on, and you do something that depends on that. Then there's a distinction between arbitrary operations and those operations which care about the details of that microstate.
Yes.
But if you have just one theory, everything is just numbers. Like what does it mean to depend on the microstate? Or like it's not very clear how to make that sharp at all. Like how do you distinguish operations which depend on the microstate and don't depend on the microstate? But they're just numbers.
But this operator could depend sensitively. I mean, this operator will depend sensitively.
What does that mean? Like there's some list of numbers. Like what is different about this numbers and some other numbers? I know it's computed using that, but how do I like then equally like if I just handed you these numbers, you could have just said, okay, this just does this operation on the space.
So
How do we distinguish these two things? That's the issue.
I thought you were
It's
going
the
to say,
same operation.
I thought you were going to say that you cannot make a good PETS map without significant entanglement.
There's that as well, but that we can tune by saying that S is like 1,000 or something.
Okay,
Right.
but then you get a fuzzy PETS
We
map.
get a fuzzy PETS.
And that would be part of the puzzle, right? That why is the bulk so fuzzy? I thought that was going to be
You could say that. I mean, so if, okay, then you would have to say if you take
that
that
you cannot using the PETS map make many things unless there's a lot of entanglement, right? Isn't that the case?
Yeah, I mean, then in the limit where you take S to 0, you would just have to say that
That the PETS map is failing, right?
the PETS map is failing, but the question is how do you interpret that? Does that mean that the closed universe is not encoded in the CFT, or do you say that the closed universe?
But that's a separate question. But at least that gets around the question of the PETS map, right?
Yeah, sure.
Yeah.
Fine. If S cluster was small, then there would be large.
Yeah. So I thought that is where you had a real paradox, right? Where S classical is really small.
Yeah. That's right. That's right.
Then the part of the bulk that you see from the boundary is very small.
Yeah.
And then however you see it, you'll see only a very small space.
Let me ask you the following. You didn't elaborate on the JT version of this because of lack of time.
Yeah.
But presumably, in that context of the SSS matrix model, etc., test the following, or you tell me. I take one heavy operator O and I create a closed universe, and I take another operator O prime. I create a slightly different universe, right?
Yeah.
Which we
And
will
see the overlap between them. So,
yeah,
Yeah.
and you want to ask the overlap or how are they different?
Yeah.
Right?
Yeah.
And this, as you said now, I understand your comments will translate to how are your CI alpha betas
Yeah.
different.
I mean, roughly speaking, what's going to happen is you have two different O's, O and O prime. You're projecting them down into this small Hilbert space. There's a large number of O's, but there's a small Hilbert space. They're going to have some small overlap. They're basically like picking random states within the small low energy band. They're going to have small overlap, but I mean, if you compute the square and so on, then it's going to be some large.
So it'll be some, hopefully, if what you're saying is true, it'll be random, but not fully random.
Yeah, there should be some more
version of
structure.
pseudo-random. That is, what is the structure
Yeah.
of departure from randomness?
Yeah.
It should be a calculable thing.
Yeah.
What do
Yeah.
you feel?
Yeah. Should be calculable.
Because that's where the information of the interior will lie.
Yeah, we can talk about this later, but I mean, I'm just saying that in the current setup that's been constructed in JD, the entanglement is like relatively large. And because of that, it's going to be parametrically small in that parameter. But yeah, modulo that, I mean, there should be a better version.
You mean you can't set up the case where it's relatively few operators?
At least so far, it hasn't been set up. Yeah, we can talk. I mean, it's basically because JT is what you need to first do is get a thermal AdS like sector in JT. JT doesn't have that, right? JT just has a continuous spectrum starting from energy 0. So you need to somehow deform JT to have a gap with a small set of states and then do that. We can talk about this.
Okay. But in some version, if you could do it, right?
You can try
The question to translate to those departures from complete randomness.
But there you would just, I mean, it wouldn't be you would just say this, just say AdS not equal to CFT. You'd say that thing is done in the Hartle-Hawking state, it's computing averages over those coefficients. The other thing is computed in a fixed alpha, these are just different things.
So, I mean,
once you have non-trivial couplings on the boundary, there's no puzzle at all.
right. So wouldn't the conclusion coming out of this be that if you had a setup where you didn't have an ensemble average but just a single CFT, then UV effects would have to kill off your extra.
Exactly. That thing we don't understand, and that may be something we may be able to address. What you want to understand is how fixed alpha, the gravitational path integral can give you description too. We don't have any clear way to get that. Right? It would have to involve some new effects like half hormones or something like that. That would be a very interesting thing to try to understand. Yeah.
Okay. Yeah. But I mean, at least if we flesh it out in some lower dimensional models, that
Yeah, no,
the pseudo run, whatever, then if it's not present because you have a single alpha, it suggests that maybe you say it already less, but anyway, yeah.
All right. That's 9%.